Right now, as you read these words, you might be sitting inside the most massive black hole imaginable. Not metaphorically, not as a thought experiment. Literally inside a black hole where the event horizon surrounds our entire observable universe. And the Big Bang wasn't the beginning of everything, but rather the moment we crossed the point of no return into an infinitely vast cosmic trap. This isn't science fiction. It's a legitimate scientific hypothesis proposed by respected physicists, backed by mathematics, and supported by some surprisingly compelling evidence. The idea sounds absurd at first. Black holes are supposed to be cosmic vacuum cleaners that devour light and matter, crushing everything into a singularity where physics breaks down. How could we possibly live inside one? Wouldn't we notice? Wouldn't everything be falling inward toward a crushing center? But here's the thing. The physics of a black hole's interior, when you actually work through the mathematics of general relativity, looks disturbingly similar to the physics of our expanding universe. The equations that describe how space and time behave inside a black hole closely match the equations cosmologists use to describe the evolution of the cosmos. This theory emerged in 1992 when physicist Lee Smolin published a paper suggesting that black holes might give birth to new universes, and that our universe might be the interior of a black hole that formed in some parent universe. The idea was initially dismissed as speculative, but over the following decades, multiple physicists independently arrived at similar conclusions through different routes. Polish physicist Nikodem Popławski refined the theory in the 2010 seconds, showing that if you include torsion, a geometric property of spacetime predicted by Einstein-Cartan theory, black holes naturally produce expanding universe interiors that look exactly like our cosmos. What makes this theory so compelling isn't just mathematical elegance. It solves real problems that have plagued cosmology for decades. Why did the Big Bang happen? Standard cosmology has no answer. It simply asserts that the universe began in an infinitely dense state for no particular reason. But if we're inside a black hole, the Big Bang is explained. It's the moment when matter in the parent universe collapsed through an event horizon. Why does the universe expand? Standard cosmology invokes dark energy and inflation, mysterious phenomena we don't fully understand. But black hole interiors naturally expand due to the geometry of space-time inside the event horizon. Why is the cosmic microwave background so uniform across the entire sky? Standard cosmology requires inflation, a period of exponentially rapid expansion to smooth out irregularities. But inside a black hole, all matter that crosses the event horizon is causally connected through the singularity, potentially explaining the CMB's uniformity without invoking inflation. Why does the observable universe have roughly the same mass and size as certain types of black holes? Coincidence, says standard cosmology. Natural consequence of being inside one, says the black hole universe theory. The implications are staggering. If we're inside a black hole, then every black hole in our universe might contain an entire universe with its own galaxies, stars, and potentially civilizations. Black holes wouldn't be endpoints where information is destroyed, but rather gateways to new realms of existence. The multiverse wouldn't be a speculative fantasy, but an inevitable consequence of black hole physics. Every time a massive star collapses and forms a black hole, a new universe with its own physical laws potentially springs into existence. This theory also suggests that time itself works differently than we think. Outside our black hole, in the parent universe, only an instant might have passed since our universe formed, even though 13.8 billion years have elapsed inside. Time dilation near event horizons is extreme in general relativity, and observers outside a black hole see time inside slow to a crawl. From their perspective, we're frozen at the moment of crossing the horizon. From our perspective inside, billions of years unfold as space expands and galaxies form. Drop it in the comments below where in the world you're watching from and what time it is there. Now, prepare yourself for a journey through the looking glass, where inside becomes outside, where black holes are wombs rather than graves, and where the boundary between our universe and others might be thinner than the width of a proton. We're going to explore the evidence, examine the mathematics, confront the objections, and ask whether we can ever know for certain if this wild idea is true, the moment you realize everything might be inside out. The journey to understanding the black hole universe theory begins with a simple but profound question. What does space-time look like inside a black hole? Most people's intuition about black holes comes from popularizations that emphasize the crushing gravitational forces and the inevitability of being drawn toward the singularity. These descriptions are accurate but incomplete. They focus on what happens to objects inside the black hole, but rarely describe the geometry of space-time itself from the perspective of someone living in that interior. General relativity, Einstein's theory of gravity, describes gravity not as a force, but as the curvature of space-time. Massive objects warp the fabric of space and time, and other objects move along the straightest possible paths through this warped geometry. A black hole represents an extreme case where space-time is warped so severely that not even light can escape from inside a certain boundary called the event horizon. The event horizon isn't a physical surface, but rather a point of no return, a place where the escape velocity exceeds the speed of light. The mathematical description of a black hole comes from solutions to Einstein's field equations. The simplest solution, found by Karl Schwarzschild in 1916, just months after Einstein published general relativity, describes a non-rotating, spherically symmetric black hole. The Schwarzschild solution includes both the exterior region outside the event horizon and the interior region inside it. The exterior is familiar. Time flows forward, space extends in all directions, and objects can in principle escape to infinity. But the interior is bizarre. Inside the Schwarzschild horizon, the roles of time and space flip. The radial direction, pointing toward the singularity, becomes time-like rather than space-like. This means that moving toward the singularity isn't a spatial choice, but a temporal inevitability, just as moving forward in time is inevitable for us outside. You can no more avoid approaching the singularity once inside than you can avoid moving into the future. Conversely, what was the time coordinate outside becomes a space-like coordinate inside, meaning that observers inside can, in principle, access different times in their spatial coordinates. This coordinate reversal has profound implications. In the black hole's interior, space naturally expands in 2 of the 3 spatial directions, while contracting in the 3rd direction, pointing toward the singularity. An observer inside, if they could somehow avoid being torn apart by tidal forces, would see space around them stretching and expanding exactly like the expansion of our universe. The mathematics is essentially identical to the Friedmann-Lemaitre-Robertson-Walker metric, the solution cosmologists use to describe our expanding universe. In 1966, Mendel Sachs pointed out this mathematical similarity, noting that the interior of a Schwarzschild black hole could be interpreted as an expanding universe. But he didn't develop the idea fully, and it was largely forgotten. The similarity was rediscovered by several researchers over subsequent decades, but each time it was treated as a mathematical curiosity rather than a serious physical proposal. After all, the Schwarzschild interior includes a singularity, a point where curvature becomes infinite and physics breaks down. Surely no one actually lives inside such a solution. The breakthrough came when physicists realized that quantum effects and modifications to general relativity might eliminate or alter the singularity. If space-time, at very small scales, has additional structure, such as torsion or quantum foam, the infinite compression at the singularity might be avoided. The collapsing matter might bounce or spread out, creating a smooth interior geometry without a singularity. In such a scenario, the black hole's interior could genuinely be a livable space, a region where matter and energy evolve according to physical laws, forming structures like stars and galaxies. Lee Smolin, in his 1992 work on cosmological natural selection, proposed that this is exactly what happens. Black holes don't crush matter into singularities, but rather channel it into new, expanding universes. The Big Bang that we observe in our past is actually the view of the black hole's event horizon as seen from inside. The rapid early expansion we call inflation is the natural expansion of the black hole's interior spacetime. The matter and energy in our universe are the remnants of whatever fell into the black hole from the parent universe. This inversion of perspective changes everything. We usually think of black holes as objects in our universe, things we can study from the outside. But if we're inside one, we can never see the outside. The event horizon surrounds us at the edge of the observable universe. Though we can't see it directly, we experience its effects as the cosmological horizon, the boundary beyond which light hasn't had time to reach us since the Big Bang. The parent universe, where our black hole formed, would be forever inaccessible to us, separated by a one-way membrane in space-time. The moment of realization that this might be true is simultaneously exhilarating and unsettling. Exhilarating because it provides elegant answers to profound questions about cosmic origins. Unsettling because it suggests that objective reality is far stranger than we imagined, that the universe isn't a box we inhabit, but potentially an interior we can never escape. Everything we see, from the cosmic microwave background to the most distant galaxies, would be features of a black hole's interior, elaborate structures arising from the interplay of matter, energy, and warped space-time within a region that, from the outside, appears as nothing more than a gravitational anomaly. Lee Smolin's 1992 paper that changed cosmology forever. In 1992, Lee Smolin, a theoretical physicist at the Perimeter Institute, published a bold and controversial paper titled "Did the Universe Evolve?" The paper appeared in Classical and Quantum Gravity and proposed an audacious idea that universes reproduce through black holes, and that the laws of physics in our universe are the result of a cosmic evolutionary process analogous to natural selection in biology. While the evolutionary aspect of Smolin's theory remains speculative, the paper introduced a mechanism that would reshape how some physicists think about black holes and cosmic origins. Smolin's central proposal was that when a black hole forms, it doesn't simply crush matter into a singularity, but instead gives birth to a new, expanding universe. This new universe exists inside the black hole, but is causally disconnected from the parent universe. From the perspective of observers in the parent universe, the black hole appears as a normal black hole with an event horizon and a finite mass. But from the perspective of observers inside, they experience an expanding universe with its own space-time, matter, and physical evolution. The mechanism Smolin proposed relied on quantum gravity effects near what would classically be the singularity. In classical general relativity, matter falling into a black hole is compressed to infinite density at a singular point. But quantum mechanics suggests that at extremely small scales, roughly the Planck length of 10 to the negative 35 meters, The smooth fabric of space-time breaks down into a quantum foam of fluctuating geometry. At these scales, the singularity might be resolved, meaning the infinite compression is avoided and matter instead undergoes a bounce or transition to a new expanding phase. Smolin suggested that quantum effects cause the collapsing matter in the black hole to rebound, creating an expanding universe on the other side of what would have been the singularity. This expanding universe inherits some properties from the parent universe, including most of the physical constants and laws, but with small random variations. These variations arise because the quantum bounce involves inherent uncertainties that affect how the new universe's parameters are set. Over many generations of black hole formation and universe creation, physical laws would evolve through a selection process. The selection mechanism works as follows. Universes whose physical laws favor the formation of many black holes will have many offspring universes with similar laws. Universes whose laws don't favor black hole formation will have few offspring. Over countless generations, the multiverse would become dominated by universes fine-tuned to produce black holes efficiently. Smolin argued that this could explain why our universe's physical constants seem fine-tuned for complexity. Stars, which produce black holes, require specific values of constants to form, and those same constants allow for complex chemistry and potentially life. Smolin's paper was controversial for several reasons. First, it required quantum gravity effects that weren't fully understood. In 1992, string theory was the dominant approach to quantum gravity, but it didn't obviously predict the kind of singularity resolution Smolin needed. Loop quantum gravity, another approach that Smolin helped develop, seemed more promising, but it was still in early stages. Critics argued that Smolin was speculating about physics beyond current knowledge. Second, the evolutionary mechanism seemed untestable. How could we ever know if other universes exist inside black holes? How could we measure whether physical constants vary between universes? Without testable predictions, critics argued, the theory was more philosophy than physics. Smolin responded that the theory did make predictions. It predicted that our universe's physical constants should be near optimal for producing black holes, and any tweaking of the constants should reduce black hole production. Some of these predictions could in principle be tested by studying how changes to constants would affect stellar evolution. Third, many physicists were uncomfortable with the idea that our universe is inside a black hole. The standard Big Bang model, though incomplete, was well established and supported by vast amounts of evidence. Proposing that the Big Bang was actually a transition through a black hole event horizon seemed to complicate rather than clarify cosmic origins. What caused the parent black hole to form? What existed before the parent universe? Smolin's theory seemed to push the origin question back rather than answer it. Despite these objections, Smolin's paper sparked interest in the possibility that black hole interiors could be described by expanding cosmological models. Several physicists began exploring related ideas, examining the mathematical connections between black hole interiors and cosmological solutions more carefully. Over the following 2 decades, research by Nicodem Popławski, Raul Carballo-Rubio, and others would build on Smolin's foundation, adding mathematical rigor and addressing some of the original criticisms. One key insight that emerged from follow-up work was that you don't necessarily need quantum gravity to connect black holes and universes. Classical general relativity itself, when extended to include torsion through Einstein-Cartan theory, naturally produces expanding universes inside rotating black holes. This moved the idea from the realm of speculative quantum gravity to a potentially testable prediction of a specific modification to general relativity. If Einstein-Cartan theory is correct, and if space-time has torsion at high densities, then black holes automatically give birth to universes. Smolin's paper also introduced the philosophical concept of the fecund universe, a cosmos that reproduces and evolves. This shifted thinking away from the idea that our universe is unique or fundamental, and toward a picture where universes are common, perhaps even ubiquitous. Every black hole becomes a potential parent, every universe a potential offspring. The multiverse, in this view, isn't just a collection of disconnected bubble universes produced by eternal inflation, but a connected genealogy of universes descended from one another through black holes. By 2020, Smolin's ideas had influenced enough research that major conferences included sessions on black hole cosmology and universe reproduction. While still not mainstream, the theory had achieved a level of respectability, attracting serious investigation from cosmologists and quantum gravity theorists. Whether Smolin's specific evolutionary mechanism operates remains uncertain, but his broader claim that black hole interiors might be universes has become a legitimate area of scientific inquiry, studied with the tools of general relativity, quantum field theory, and observational cosmology. The Big Bang singularity versus the black hole singularity. Suspicious twins. At the heart of the black hole universe theory lies a striking mathematical fact. The equations describing the Big Bang singularity are nearly identical to the equations describing a black hole singularity. Both involve infinite densities, both mark boundaries where classical general relativity breaks down, and both involve extreme curvatures of space-time. This similarity is more than coincidence. It suggests a deep connection between these two seemingly different phenomena. In standard Big Bang cosmology, the universe begins in a singularity at time zero. Going backwards in time from the present, we find the universe was smaller and denser in the past. At about 380,000 years after the Big Bang, the universe cooled enough for atoms to form, releasing the cosmic microwave background radiation. Before that, during the first few 100,000 years, the universe was a hot plasma. Going back further to the first seconds, nuclear reactions formed light elements like hydrogen and helium, and further back, still to fractions of a second, particle physics processes created the matter and antimatter that filled the early universe. But what about time zero itself? The equations of general relativity, combined with the observed expansion of the universe, imply that if we extrapolate backward to t equals 0, we reach a state of infinite density and temperature. At this singularity, the curvature of spacetime becomes infinite, quantum effects become dominant, and our equations cease to make sense. We simply don't know what happened before the Big Bang, or even whether the question makes sense, because time itself may not have existed. Compare this to a black hole singularity. When matter collapses to form a black hole, it creates an event horizon surrounding a region of increasingly warped space-time. Classical general relativity predicts that the collapsing matter is compressed without limit, forming a singularity where density and curvature become infinite. Just like the Big Bang singularity, the black hole singularity marks a boundary where our theories break down. The laws of physics, as we know them, cannot describe what happens at the singularity. Roger Penrose and Stephen Hawking proved in the 1960 seconds that singularities are generic in general relativity. Their singularity theorems showed that under reasonable assumptions about matter and energy, gravitational collapse inevitably produces singularities. The theorems apply both to collapsing matter, forming black holes, and to the universe in reverse time leading to the Big Bang. Mathematically, these are closely related scenarios. Both involve space-time curvature growing without bound as you approach a particular point or moment. The similarity extends to the metrics. the mathematical descriptions of space-time geometry. The Friedmann-Lemaitre-Robertson-Walker metric, which cosmologists use to describe the universe's large-scale structure, describes a homogeneous, isotropic expanding space. This metric contains a scale factor that grows with time, causing distances between galaxies to increase. As you trace this scale factor backward to t equals 0, it goes to 0, indicating that all of space was compressed to a point. Inside a black hole, the situation is reversed in a sense. For a Schwarzschild black hole, the interior metric shows that the radial direction becomes time-like and the time direction becomes space-like. The singularity sits not at a point in space, but at a moment in the future for any observer inside. As time progresses inside the black hole, the observer is inevitably drawn toward the singularity. If we flip our perspective and think of the singularity as the starting point rather than the end point, we get something that looks like an expanding universe beginning from a singular state. This flipped perspective is precisely what the black hole universe theory proposes. What we experience as the forward direction of time inside the black hole corresponds to expansion from the singularity. The Big Bang is the singularity viewed from one side, from inside the black hole. The crushing compression toward a singularity that an outside observer would calculate for matter falling in is, from the inside, experienced as expansion from a singularity. The mathematics is the same, just with different interpretations of the time and space coordinates. One might object that black hole singularities and the Big Bang singularity have different topologies and properties. A Schwarzschild black hole singularity is space-like, meaning it lies to the future of all points inside the event horizon. The Big Bang singularity is often described as time-like, meaning it lies in the past of all events in our universe. A rotating Kerr black hole has a ring singularity rather than a point singularity. These differences might seem to rule out the identification of black hole and cosmological singularities. However, these differences arise in part from the choice of coordinates and the specific solutions considered. General relativity allows many different coordinate systems, and singularities can appear different depending on which coordinates you use. Moreover, realistic black holes and realistic cosmological models include complications like rotation, asymmetries, and quantum effects that modify the simple, idealized solutions. When these complications are included, the distinctions between types of singularities become less sharp. Furthermore, most physicists believe that singularities aren't real physical entities, but rather indicate the breakdown of classical general relativity. At the extreme densities near singularities, quantum gravity effects should become important, potentially removing or modifying the singularities. Loop quantum cosmology, for instance, replaces the Big Bang singularity with a bounce, where the universe contracts to a minimum size and then expands. Similar bounces might occur inside black holes, removing their singularities and creating smooth transitions to expanding interiors. If singularities are removed by quantum effects, then the distinction between black hole and cosmological singularities becomes even less meaningful. Both are classical artifacts that disappear in a more complete quantum theory. What remains is the geometry of space-time far from the singularity, and this geometry can be similar for black hole interiors and cosmological spacetimes. The black hole's interior can genuinely function as an expanding universe without the pathologies of a singularity. The parallel between black hole and Big Bang singularities suggests that these aren't two unrelated phenomena, but two aspects of the same underlying physics. If our universe emerged from a black hole singularity in a parent universe, then the Big Bang is explained as a consequence of black hole formation elsewhere. The mystery of why the universe began isn't eliminated, but it's transformed. Instead of asking why our universe began, we ask why black holes form in the parent universe and what caused the chain of universes to begin. The question is pushed back, but possibly becomes more tractable. Event horizons and cosmic horizons. The same mathematical structure. One of the most compelling pieces of evidence for the black hole universe theory comes from the mathematical equivalence between event horizons around black holes and cosmological horizons in expanding universes. These two seemingly different boundaries share the same fundamental structure in general relativity, suggesting they might be two perspectives on the same physical entity. Understanding this equivalence requires examining what horizons are and how they arise from the geometry of space-time. An event horizon around a black hole is a null surface, a boundary formed by light rays that hover at the edge of escaping. Light emitted from just inside the horizon can never escape to infinity. Light emitted from just outside can escape, though highly redshifted. The horizon marks the point of no return. Mathematically, it's defined as the boundary of the past light cone of future null infinity, meaning it separates events that can send light signals to distant observers from events that cannot. A cosmological horizon, also called a particle horizon, arises in expanding universes. As the universe expands, light from distant regions takes time to reach us. There's a maximum distance from which light has had time to travel since the Big Bang. Regions beyond this distance are outside our cosmological horizon. We cannot see them because their light hasn't reached us yet. As time progresses, the cosmological horizon expands, bringing more of the universe into view, but there's always a boundary beyond which we cannot see. The mathematical descriptions of these horizons are remarkably similar. Both are null surfaces, meaning they're formed by light rays. Both divide space-time into causally connected and causally disconnected regions. Both exhibit temperature and entropy in thermodynamic descriptions of black holes and cosmology. Both involve information paradoxes about what happens to information beyond the horizon. The equations governing their properties are, in many cases, identical up to coordinate transformations. The most striking example of this equivalence comes from de Sitter space, a solution to Einstein's equations describing an empty universe with a positive cosmological constant. De Sitter space expands exponentially, much like our universe did during inflation. An observer in de Sitter space sees a cosmological horizon at a fixed distance, beyond which they cannot observe events. This horizon has temperature and entropy, radiating what's called Gibbons-Hawking radiation, by analogy with Hawking radiation from black holes. Now consider the geometry of de Sitter space more carefully. Mathematically, it has the same structure as the interior of a black hole with a cosmological constant. The cosmological horizon in de Sitter space corresponds to the event horizon of the black hole when viewed from outside. An observer inside sees an expanding universe with a horizon they cannot cross. An observer outside sees a black hole with an event horizon surrounding a region they cannot access. These are two descriptions of the same geometry, related by coordinate transformations. This duality between black hole and cosmological descriptions appears in other contexts as well. The anti-de Sitter conformal field theory correspondence, or ADS CFT, one of the most important developments in theoretical physics in the past 3 decades, relates gravity in anti-de Sitter space to quantum field theory on the boundary. This correspondence suggests that space-time geometry and event horizons might be emergent phenomena arising from quantum information and entanglement. Black hole horizons and cosmological horizons could be two manifestations of the same underlying quantum structure. Another connection comes from the holographic principle, which states that the information content of a region of space is encoded on its boundary. For a black hole, the information is encoded on the event horizon, with the entropy proportional to the horizon's area. For a cosmological horizon, similar considerations apply. The information accessible to an observer is limited by the horizon area, suggesting a holographic bound. This parallel reinforces the idea that event horizons and cosmological horizons are fundamentally similar. Temperature provides yet another parallel. Stephen Hawking showed in 1974 that black holes emit thermal radiation with temperature inversely proportional to their mass. This Hawking temperature arises from quantum field theory in curved spacetime, with particle-antiparticle pairs created near the event horizon. One particle escapes while the other falls in, producing a net outward radiation flux. Cosmological horizons in accelerating universes also have associated temperatures, with radiation that observers detect as a thermal bath. If our universe is inside a black hole, these parallels make perfect sense. The cosmological horizon we observe at the edge of the visible universe would literally be the black hole's event horizon, viewed from inside. When we look toward the horizon, we're looking toward the boundary that separates us from the parent universe. The Hawking radiation from the event horizon would manifest inside as the cosmic microwave background, or as vacuum fluctuations. The entropy of the cosmological horizon would be the entropy of the black hole event horizon, measured from outside. This identification resolves some puzzles. Why does the cosmological horizon have entropy at all? In standard cosmology, it's a somewhat mysterious feature arising from quantum field theory in curved spacetime. But if the horizon is a black hole event horizon, the entropy is natural. It's the black hole's entropy. Why does the horizon have a temperature? Again, standard cosmology requires quantum field theory in curved spacetime to explain it. But in the black hole picture, it's Hawking radiation, a well-established, though not yet observed, phenomenon. The equivalence also suggests observational tests. If the cosmological horizon is a black hole event horizon, it might have specific properties we can measure. For instance, the relationship between horizon area and entropy might show deviations from the standard formula if quantum gravity effects are important. The spectrum of vacuum fluctuations might have subtle features reflecting the event horizon structure. The polarization of the cosmic microwave background might encode information about how the event horizon formed and how matter crossed it. Of course, not all cosmological horizons are exactly like black hole event horizons. Our universe has a past boundary, the Big Bang, that doesn't obviously correspond to anything in standard black hole physics. Our cosmological horizon is expanding and changing as the universe evolves, whereas a stationary black hole's event horizon is fixed. These differences require explanation in the black hole universe theory, either through dynamical black hole models or through modifications to general relativity that change event horizon properties. Despite these complications, the mathematical equivalence between horizons remains a powerful hint that black holes and universes are more intimately connected than standard models assume. Every time physicists calculate properties of cosmological horizons, they're essentially calculating properties of event horizons. Every phenomenon associated with black hole event horizons, from Hawking radiation to entropy to information paradoxes, has a parallel in cosmology. This convergence of structures across seemingly different domains of physics suggests a deep underlying unity, one that the black hole universe theory attempts to explain. Why the universe expands, black hole interior dynamics, explained. The expansion of the universe is one of the most firmly established facts in cosmology. Galaxies are moving away from each other, and the farther apart they are, the faster they recede. This expansion is described by the scale factor in cosmological models, a number that increases with time and tells us how distances between objects grow. But why does the universe expand? Standard cosmology treats expansion as a boundary condition, something that was set at the Big Bang for reasons we don't fully understand. The black hole universe theory offers a different explanation. The universe expands because expansion is the natural behavior of space-time inside a black hole's event horizon. To understand this, we need to examine the geometry inside a black hole more carefully. The Schwarzschild solution, which describes a non-rotating black hole, provides the simplest case. Outside the event horizon, the metric has the familiar form where time is time-like and the radial coordinate is space-like, but inside the horizon, these roles reverse. The radial coordinate becomes time-like, meaning it functions like time, flowing inevitably inward toward the singularity. The time coordinate becomes space-like, meaning it functions like space, extending in different directions. This coordinate reversal has a startling consequence. Inside the black hole, all observers must experience decreasing radial coordinate as time progresses. If we identify the radial coordinate with a scale factor describing the size of space, then this radial decrease corresponds to space contracting. But wait, didn't we just say the universe expands? The resolution lies in perspective. From outside, matter falling into the black hole is compressed toward the singularity. But from inside, if we set up coordinates appropriate to the interior observers, the same geometry describes an expanding space. Think of it this way. Inside the black hole, the singularity lies to the future, not at a point in space. As time progresses, all of space approaches this future singularity. But approaching the singularity from inside can manifest as expansion in appropriate coordinates. Different regions of the interior can be separated by growing distances, even as they all head toward the same ultimate fate. This is analogous to how different points on the surface of an inflating balloon move apart from each other, even though they're all attached to the same surface. Mathematically, the interior of a Schwarzschild black hole can be described by a metric identical to the flat Friedmann-Robertson-Walker metric used in cosmology. The scale factor grows with the time coordinate inside the black hole. Space expands homogeneously and isotropically, meaning it expands the same way in all directions and at all locations, just like our universe. The expansion is driven not by any external force, but by the geometry of space-time itself, specifically by the warping caused by the initial matter that collapsed to form the black hole. This resolves one of cosmology's deepest mysteries. Why does space expand rather than contract or remain static? In standard cosmology, expansion is imposed as an initial condition. We observe that the universe is expanding, so we run the equations backward and find it must have been denser and hotter in the past, eventually reaching the Big Bang. But we don't explain why it expands. We simply assert that it does. General relativity allows contracting and static solutions as well as expanding ones, so expansion is a choice, not a necessity. Inside a black hole, expansion becomes necessary rather than contingent. The geometry of the interior forces space to evolve, and the evolution takes the form of expansion when described in coordinates natural to interior observers. This makes expansion a consequence of being inside a black hole rather than a mysterious initial condition. It also suggests that the rate of expansion described by the Hubble constant in cosmology should be related to the mass and properties of the parent black hole. Nikodem Popławski showed that rotating black holes provide an even better match to observed cosmology. A rotating black hole is described by the Kerr metric, which includes angular momentum. Inside a rotating black hole, space-time has torsion, a geometric property absent in Schwarzschild solutions. Torsion allows spin and intrinsic angular momentum to affect space-time geometry. When matter with spin collapses into a Kerr black hole, Einstein-Cartan theory, which includes torsion, predicts that the interior undergoes a bounce instead of forming a singularity. The bounce creates an expanding universe on the other side of the would-be singularity. Popławski's calculations show that the expansion rate, spatial curvature, and matter density in this bounced interior match observational values for our universe. If the parent black hole has a mass comparable to the mass of our observable universe, roughly 10 to the 23 solar masses. This is an enormous black hole, far larger than any observed in our universe, but it could plausibly form in a parent universe with different physical constants or through the merger of many smaller black holes. The rotation of the parent black hole also explains why our universe has angular momentum structure at large scales. Observations show that galaxy clusters and superclusters have net angular momentum, rotating slowly about their centers. The cosmic microwave background shows subtle asymmetries that might be signatures of overall rotation. In standard cosmology, these features are puzzling because inflation should have erased any net rotation, producing a perfectly isotropic universe. But if our universe formed inside a rotating black hole, its rotation would be inherited from the parent black hole's spin, naturally explaining observed angular momentum structures. The expansion rate's evolution over time also makes sense in the black hole picture. Our universe's expansion has been accelerating for the past several billion years, a phenomenon attributed to dark energy or a cosmological constant. Inside a black hole, the expansion rate depends on how far the interior has evolved from the moment of crossing the event horizon. Early in the interior's history, matter dominates and expansion proceeds at one rate. Later, as matter dilutes, other effects like vacuum energy dominate, causing acceleration. The transition from decelerated to accelerated expansion observed in our universe matches what's expected for black hole interiors at a certain stage of evolution. One might object that black hole interiors should recollapse toward a singularity, not expand indefinitely. Classical Schwarzschild interiors do have this property. All geodesics reach the singularity in finite proper time, but modifications to general relativity, including torsion in Einstein-Cartan theory and quantum gravity effects, can alter this behavior. A bouncing cosmology inside a black hole could expand indefinitely, especially if the interior geometry includes features like a cosmological constant that drives eternal expansion. Our universe's apparent fate of eternal accelerating expansion would then reflect properties of the black hole interior we inhabit. The cosmic microwave background as Hawking radiation from the outside. The cosmic microwave background, the faint glow of radiation filling all of space, is one of the pillars of Big Bang cosmology. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, the CMB appears as a nearly uniform bath of microwave photons with a temperature of 2.725 Kelvin. Standard cosmology explains the CMB as radiation released when the universe was about 380,000 years old and cooled enough for electrons and protons to combine into hydrogen atoms. Before this recombination, the universe was a hot plasma that scattered photons continuously. After recombination, photons could travel freely, and we see them today as the CMB, redshifted by cosmic expansion from visible light to microwaves. But the black hole universe theory suggests a different origin for the CMB. It might be Hawking radiation from the event horizon of the black hole we inhabit, viewed from inside. This radical reinterpretation of the universe's most studied relic of the early universe provides testable predictions and connects cosmology to black hole thermodynamics in surprising ways. Stephen Hawking predicted in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. According to quantum field theory, particle-antiparticle pairs are constantly created from vacuum fluctuations throughout space. Normally, these pairs annihilate each other almost immediately, returning their borrowed energy to the vacuum. But near a black hole's event horizon, one particle of a pair can fall into the black hole while the other escapes to infinity. The escaping particle appears to distant observers as Hawking radiation, a thermal glow with temperature inversely proportional to the black hole's mass. For stellar mass black holes, Hawking temperatures are absurdly low, about 10 to the negative 8 Kelvin for a 1-0 solar mass black hole. Such temperatures are far below the cosmic microwave background, making Hawking radiation undetectable in practice for any astrophysical black hole. But for a black hole with a mass equal to the observable universe, roughly 10 to the 23 solar masses, the Hawking temperature would be around 10 to the negative 30 Kelvin. Still cold, but let's think about this differently. The Hawking temperature of a black hole is given by the formula where the temperature equals the reduced Planck constant times the speed of light cubed divided by 8 times pi, multiplied by the gravitational constant, the black hole's mass, and Boltzmann's constant. Here, the reduced Planck constant sets the scale for quantum effects. The speed of light and gravitational constant relate to gravity. The mass is the black hole's mass, and Boltzmann's constant connects energy to temperature. This formula applies to observers who are far away from the black hole, but observers near the horizon experience time dilation, which affects the perceived temperature of radiation. Inside the black hole, the relationship between proper time for interior observers and time measured by exterior observers involves extreme time dilation factors. These factors could translate the exterior Hawking temperature into much higher temperatures inside. Moreover, the Hawking radiation process, viewed from inside the black hole, looks different than from outside. From outside, the black hole emits thermal radiation at a steady rate. From inside, near the event horizon, in the early moments after formation, the quantum fluctuations that produce Hawking pairs would appear as a hot, dense bath of particles. This particle bath could be the source of the matter and radiation that filled the early universe, with the CMB being the cooled remnant of this initial quantum flux. Calculations by Afshordi, Mann, and Pourhassan in 2013 explored this connection more rigorously. They showed that if our universe is the interior of a black hole in a parent universe with one extra spatial dimension, the CMB properties would match observations. The extra dimension is a feature of certain theories of gravity and changes how the interior geometry works, allowing for an expanding universe that avoids singularities and produces the right CMB temperature when quantum effects are included. The CMB's near-perfect blackbody spectrum, one of its most remarkable features, also fits naturally in the Hawking radiation picture. Hawking radiation is thermal, meaning it has a blackbody spectrum by definition. The CMB spectrum, measured to extraordinary precision by the COB and Planck satellites, is the most perfect blackbody ever observed in nature. Standard cosmology explains this by saying the early universe was in thermal equilibrium, but achieving such perfect equilibrium requires very specific conditions. In the black hole picture, the blackbody spectrum is automatic, a consequence of the quantum nature of Hawking radiation. The CMB also has tiny fluctuations, variations in temperature of about 1 part in 100,000 across the sky. These fluctuations are the seeds of structure formation, growing over billions of years into galaxies and galaxy clusters. Standard cosmology attributes these fluctuations to quantum fluctuations during inflation, stretched to cosmic scales by exponential expansion. But in the black hole picture, fluctuations could arise from quantum fluctuations in the Hawking radiation process, with variations in the particle creation rates near different parts of the event horizon producing temperature differences we observe in the CMB. One specific prediction of the black hole universe theory involves the CMB's statistical properties. The fluctuations should follow a nearly scale-invariant power spectrum, meaning fluctuations at different angular scales have similar amplitudes. Observations confirm this near-scale invariance, which standard inflation also predicts. But the black hole theory makes additional predictions about departures from perfect scale invariance and about the non-Gaussianity of fluctuations, subtle statistical properties that depend on the detailed physics near the event horizon. Observations of the CMB's polarization provide another test. Photons in the CMB are partially polarized, with the polarization pattern encoding information about the early universe's dynamics. Standard cosmology predicts specific polarization patterns from Thomson scattering in the early plasma and from gravitational waves produced during inflation. The black hole universe theory predicts different patterns depending on how quantum fluctuations near the event horizon couple to electromagnetic fields. Detailed measurements of CMB polarization, such as those from the Planck satellite and upcoming ground-based experiments, can potentially distinguish between these scenarios. The horizon problem, one of the motivations for inflation in standard cosmology, also has a different resolution in the black hole picture. The problem is that widely separated regions of the CMB have almost identical temperatures despite being causally disconnected in standard Big Bang models. They couldn't have influenced each other because light wouldn't have had time to travel between them. Inflation solves this by positing that these regions were once close together and causally connected before exponential expansion separated them. But inside a black hole, all parts of the interior are connected through the singularity or through the bounce if the singularity is resolved. Matter crossing the event horizon from different points in the parent universe's collapse brings correlations into the interior. These correlations ensure that different regions of the interior universe start with similar conditions, explaining the CMB's uniformity without requiring inflation. The horizon problem is thus solved topologically by the black hole geometry rather than dynamically through exponential expansion. Nikodem Popławski's torsion theory. Spinning black holes create universes. Nikodem Popławski, a Polish-American physicist, has been one of the most prominent advocates of the black hole universe theory, developing it in a series of papers published between 2010 and 2020. Popławski's crucial contribution was showing that Einstein-Cartan theory, an extension of general relativity that includes space-time torsion, naturally produces universes inside spinning black holes without requiring speculative quantum gravity assumptions. His work transformed the black hole universe idea from a hand-waving analogy to a concrete mathematical theory with testable implications. Einstein-Cartan theory, first developed by Élie Cartan in the 1920 seconds, extends general relativity by allowing space-time to have torsion in addition to curvature. In standard general relativity, space-time has curvature caused by mass and energy, but its affine connection, the mathematical structure describing how vectors are parallel transported along curves, is torsion-free. Einstein-Cartan theory drops this assumption, allowing torsion to arise from the intrinsic angular momentum or spin of matter. Torsion is a geometric property describing how space-time twists. Imagine walking along a path in twisted space. When you return to your starting point, carrying a vector parallel to your path, the vector has rotated even if you didn't deliberately turn it. That rotation is torsion. In Einstein-Cartan theory, particles with spin, such as electrons, quarks, and neutrinos, generate torsion in their vicinity. At low densities, torsion effects are tiny and general relativity remains an excellent approximation. But at extremely high densities, approaching the Planck density of 10 to the 96 kilograms per cubic meter, torsion becomes important. Popławski showed that when matter with spin collapses to form a black hole in Einstein-Cartan theory, the torsion it generates prevents the formation of a singularity. As density increases, torsion creates a repulsive force that counteracts gravitational attraction. When density reaches a critical value related to the Planck density, the repulsion becomes strong enough to halt the collapse. The matter then rebounds, expanding rapidly in what Popławski called a big bounce. This bounce creates a new region of space-time connected to the collapsing matter's original location through what was the event horizon. From the perspective of observers in the parent universe, the collapse forms a black hole with an event horizon and an apparent singularity inside. But from the perspective of observers inside, the collapse halts and reverses, producing an expanding universe. The bounce occurs at the center of the collapsing region, and the subsequent expansion creates an interior space-time that's causally disconnected from the parent universe. The event horizon functions as a one-way membrane. Information can pass from parent to child universe, but not the reverse. The expanding interior universe has properties determined by the black hole's mass and angular momentum. A more massive black hole produces a universe with more matter and energy. A black hole with higher spin produces a universe with more angular momentum and potentially different physical constants. Popławski calculated that a spinning black hole with mass comparable to the observable universe and spin parameter, near unity, close to the maximum possible spin, produces an interior matching our universe's observed properties. Specifically, Popławski found that the interior universe has spatial curvature close to flat, consistent with observations showing our universe's curvature is very small or zero. The matter density in the interior matches our universe's average matter density of about 10 to the negative 27 kilograms per cubic meter. The expansion rate corresponds to a Hubble constant in the right range, around 70 kilometers per second per megaparsec. These matches aren't coincidental fine-tuning, but natural outcomes of the bounce dynamics in Einstein-Cartan theory. Popławski's theory also explains why our universe has more matter than antimatter. In the early universe, matter and antimatter should have been created in equal amounts, but observations show matter dominates by a wide margin. Standard models require special conditions or new physics to explain this asymmetry. But in Einstein-Cartan theory, the torsion during the bounce can couple differently to particles and antiparticles, producing a net matter excess. The amount of asymmetry depends on the spin of the collapsing matter and on details of the particle physics during the bounce. Another prediction involves the cosmological constant, the energy density of empty space that drives the universe's accelerating expansion. In standard cosmology, the cosmological constant's value is a mystery. Quantum field theory predicts it should be enormous, about 10 to the 120 times larger than observed. Yet observations show it's tiny but non-zero. Popławski showed that in Einstein-Cartan theory, the bounce naturally produces a small but positive cosmological constant related to the torsion energy density left over after the bounce. The predicted value matches observations without requiring fine-tuning. The theory makes specific predictions about the early universe that differ from standard inflation. Inflation posits that the universe underwent a brief period of exponentially rapid expansion, driven by a hypothetical inflaton field. This expansion smooths out irregularities and solves the horizon and flatness problems. But inflation requires carefully chosen potentials for the inflaton and isn't uniquely specified, giving it considerable flexibility. Einstein-Cartan bounce cosmology doesn't require inflation. The bounce itself performs some of inflation's functions, smoothing irregularities and setting initial conditions. Observational tests can potentially distinguish Popowski's theory from standard cosmology. One signature involves primordial gravitational waves, ripples in space-time produced in the early universe. Inflation predicts a specific spectrum of gravitational waves that should leave imprints on the CMB's polarization. Einstein-Cartan bounce predicts a different spectrum because the dynamics during the bounce differ from inflation. Future CMB experiments measuring polarization at small angular scales could detect these differences, providing evidence for or against the black hole origin. Another test involves the universe's overall rotation. As mentioned earlier, a spinning parent black hole imparts angular momentum to the interior universe. This should produce measurable effects. Galaxy alignments might show correlations across large scales. The CMB might have specific asymmetries in its temperature and polarization patterns, and large-scale structure might have preferred orientations. Some observations, such as the so-called axis of evil in the CMB, hint at such asymmetries, though their interpretation remains controversial. Popowski also addressed philosophical objections to the black hole universe theory. One common objection is infinite regress. If our universe is inside a black hole, what about the parent universe? Is it inside a black hole too? And what about the universe containing that black hole? The chain seems to extend infinitely, never reaching a first cause. Popowski acknowledged this, but argued that infinite regress isn't necessarily a problem. The multiverse could be eternal and infinitely nested, with no first universe. Alternatively, the chain might loop back on itself through closed time-like curves or other exotic topologies, though such scenarios require more speculative physics. By 2020, Popowski's work had inspired a small but growing research community exploring Einstein-Cartan cosmology and black hole universe scenarios. Several dozen papers had cited his work, proposing refinements, extensions, and new tests. While the theory remains outside the mainstream, it represents one of the most mathematically rigorous and physically motivated versions of the idea that we might live inside a black hole, giving physicists concrete equations to study and predictions to test rather than vague philosophical speculation. Einstein-Cartan theory. When space-time itself can twist. Einstein-Cartan theory, the mathematical framework underlying Popowski's black hole universe model, extends general relativity in a way that seems minor but has profound consequences for extreme conditions like black hole interiors and the Big Bang. Understanding this theory requires delving into the geometry of spacetime and the role of intrinsic angular momentum in gravitational physics. While the mathematics is technical, the core concepts are accessible and illuminate why torsion might be essential for understanding cosmic origins. General relativity, Einstein's 1915 theory of gravity, describes how matter and energy curve spacetime and how this curvature affects the motion of objects. The theory is based on Riemannian geometry, where spacetime is a smooth manifold with a metric tensor that defines distances and angles. The metric's curvature quantified by the Riemann curvature tensor, arises from mass and energy through Einstein's field equations. Curvature tells us how geodesics, the straightest possible paths through spacetime, converge or diverge. But Riemannian geometry assumes that spacetime's affine connection, the structure describing parallel transport, has no torsion. The affine connection tells you how to compare vectors at different points in spacetime. When you parallel transport a vector along a closed loop, it returns to its starting point unchanged if the connection is torsion-free, though it might be rotated due to curvature. Torsion, if present, would cause additional rotation independent of curvature. Élie Cartan, a French mathematician who pioneered the study of differential geometry, realized in the 1920 seconds that there's no fundamental reason to require spacetime's connection to be torsion-free. In 1922, shortly after Einstein developed general relativity, Cartan proposed extending the theory to include torsion. His idea was that just as mass energy creates curvature, intrinsic angular momentum or spin might create torsion. Elementary particles have spin, an intrinsic quantum property analogous to rotation, and Cartan suggested this spin couples to spacetime geometry through torsion. Einstein initially dismissed the idea. He had briefly considered torsion but concluded it was unnecessary. The standard formulation of general relativity, using the Levi-Civita connection, which is torsion-free and metric compatible, worked perfectly for all applications anyone could think of in the 1920 seconds and 1930 seconds. Torsion seemed like mathematical complication without physical motivation. But in the 1960 seconds and 1970 seconds, physicists revisited Cartan's proposal as quantum field theory and particle physics developed, revealing that spin is a fundamental property of matter. Dennis Sciama and Tom Kibble independently developed modern Einstein-Cartan theory in the late 1960 seconds, working out the field equations and showing how spin density acts as a source for torsion. The torsion tensor, which has 24 independent components in four-dimensional spacetime, is algebraically determined by the spin density of matter. This contrasts with curvature, which is dynamical and propagates as gravitational waves. Torsion is non-propagating. It's present wherever spinning matter exists, but doesn't spread beyond. At everyday densities, torsion effects are utterly negligible. The spin density of matter, even in dense materials like neutron stars, is far too low to produce measurable torsion. Calculations show that torsion becomes significant only at densities approaching the Planck density, roughly 10 to the 96 kilograms per cubic meter. Such densities likely existed only in the first instance of the Big Bang or at the would-be centers of black holes. This is why torsion doesn't affect any terrestrial or astrophysical observations we've made so far, but could be crucial for understanding extreme conditions. The key insight is that torsion modifies the behavior of spacetime at ultra-high densities. In general relativity, gravitational collapse proceeds inexorably to a singularity where density and curvature become infinite. But in Einstein-Cartan theory, as density increases and spin density grows, torsion generates a repulsive force. This repulsion arises because the torsion-modified energy-momentum tensor includes terms proportional to the square of the spin density, and these terms can act like a negative pressure resisting compression. When density reaches a critical threshold, typically a few percent of the Planck density, the torsion-induced repulsion becomes strong enough to halt the collapse. The matter undergoes a bounce, reversing from contraction to expansion. This bounce avoids the singularity, replacing it with a smooth maximum density. The bounce is effectively a quantum gravitational effect, though it arises in a semi-classical theory where quantum matter, with its intrinsic spin, couples to classical but torsion-modified spacetime. The bounce scenario has implications for both black holes and cosmology. For black holes, it means the interior doesn't end in a singularity, but instead transitions to an expanding region. This expanding region is the new universe. For cosmology, it means the Big Bang singularity is replaced by a bounce from a previous contracting phase, possibly from a parent universe or from an earlier cycle of our own universe. The bounce provides a mechanism for creating universes without requiring a true beginning from nothing. Einstein-Cartan theory also offers solutions to several theoretical problems. The information paradox, which asks what happens to quantum information that falls into a black hole, can be addressed if black holes have interiors that evolve into universes rather than crushing everything into singularities. Information isn't destroyed, but rather passes into the new universe, where it contributes to the initial conditions. Similarly, the cosmological constant problem, the discrepancy between theoretical and observed vacuum energy density, might be alleviated if torsion effects during the bounce set the cosmological constant's value dynamically. The theory does face challenges. Observational tests are difficult because torsion effects are confined to regimes we can't directly probe. We can't observe inside black holes, and we can't recreate Planck-scale densities in laboratories. Indirect tests must rely on subtle signatures in cosmological observations, or on consistency checks with quantum gravity theories. Some physicists worry that Einstein-Cartan theory, while mathematically consistent, is merely pushing our ignorance back to slightly lower densities without resolving fundamental issues about quantum gravity. Another concern is that Einstein-Cartan theory is a classical theory, not a quantum one. It treats matter quantum mechanically. Matter has spin. But space-time classically, torsion is a classical field. A fully quantum theory of gravity would treat space-time itself quantum mechanically, and torsion might emerge as an effective description of some deeper quantum structure. Loop quantum gravity, for instance, includes torsion in some formulations, but the relationship between Einstein-Cartan theory and loop quantum gravity remains an active research area. Despite these uncertainties, Einstein-Cartan theory provides the most concrete framework currently available for modeling black hole interiors that give birth to universes. It makes specific, quantitative predictions that can be compared to observations. It connects to established physics, particularly general relativity and quantum field theory, rather than invoking entirely new principles. And it suggests that one of spacetime's most basic properties, its affine connection, might have a richness we've overlooked because we've focused on regimes where that richness doesn't manifest. The Planck epoch. Inside the universe's first tick of time, the Planck epoch, the earliest period in the universe's history, extends from time zero to approximately 10 to the negative 43 seconds after the Big Bang. During this unimaginably brief interval, the universe would have had densities and temperatures so extreme that our current theories of physics, including general relativity and quantum field theory, break down. Understanding what happened during the Planck epoch requires a theory of quantum gravity, which we don't yet have. But the black hole universe theory, particularly in its Einstein-Cartan incarnation, offers specific proposals for Planck epoch physics that connect to the black hole formation process in the parent universe. The Planck time, 10 to the negative 43 seconds, is defined as the time it takes light to travel the Planck length, 10 to the negative 35 meters, which is the scale where quantum gravitational effects become dominant. Below this scale, space-time itself fluctuates quantum mechanically, and the classical concept of a smooth space-time manifold breaks down. The Planck density, 10 to the 96 kilograms per cubic meter, is the density at which gravitational energy density equals quantum mechanical uncertainties. At these scales, gravity can no longer be treated classically. In standard Big Bang cosmology, we extrapolate backward from the earliest times we can confidently model, around 10 to the negative 10 seconds when the electroweak interaction unified, to earlier epochs where temperatures and densities increase without bound. At the Planck time, the temperature would have been 10 to the 32 Kelvin, far beyond any energy scales accessible to particle accelerators. All four fundamental forces, gravity, electromagnetism, weak nuclear force, and strong nuclear force, would have been unified into a single force described by a theory of everything we don't possess. The Planck epoch is often described as a quantum foam of fluctuating spacetime, where causal structure breaks down and concepts like before and after lose meaning. Some theories suggest spacetime might have additional dimensions at these scales, or that it's discrete rather than continuous, or that it emerges from a more fundamental non-spatiotemporal structure. Without experimental guidance, these ideas remain speculative, constrained only by mathematical consistency and aesthetic principles. The black hole universe theory provides a different picture of the Planck epoch. In this view, the Planck epoch corresponds to the bounce that occurs at the center of the collapsing black hole in the parent universe. As matter collapses and density approaches the Planck scale, torsion effects become large enough to halt and reverse the collapse. The Planck epoch is the turnaround point, the moment of maximum density and minimum volume, after which expansion begins. This bounce is not instantaneous, but occurs over a timescale comparable to the Planck time. During this time, quantum effects are fully dominant, and the classical space-time picture breaks down. But unlike in standard cosmology, where the Planck epoch is the beginning with nothing before it, in the black hole picture there is a before, the collapse phase where matter fell toward what would classically be a singularity. The bounce connects the collapsing phase to the expanding phase, providing continuity across what standard cosmology treats as an impenetrable boundary. The quantum state during the bounce determines the initial conditions for the expanding universe. Quantum fluctuations during the bounce set the distribution of matter and energy, the values of physical constants, and the properties of fields that will later drive cosmic evolution. These fluctuations arise from the inherent uncertainties in quantum mechanics applied to gravitational and matter fields at Planck scales. Small variations in the bounce dynamics amplify into large-scale structures we observe today, such as galaxies and galaxy clusters. One specific prediction involves the primordial power spectrum, the distribution of density fluctuations as a function of scale. Observations of the cosmic microwave background and large-scale structure show that the primordial power spectrum is nearly scale invariant, meaning fluctuations at different scales have similar amplitudes. Standard inflation explains this through the dynamics of the inflaton field, but the black hole bounce can also produce scale invariance through quantum fluctuations during the Planck epoch. The detailed shape of the power spectrum differs slightly between models, offering a potential observational test. The bounce also affects gravitational waves produced in the early universe. Quantum fluctuations during the bounce generate gravitational waves spanning a wide range of frequencies. The spectrum of these primordial gravitational waves encodes information about the bounce dynamics and the quantum state at Planck scales. Future gravitational wave observatories, particularly space-based detectors like LISA or next-generation pulsar timing arrays, might detect primordial gravitational waves and test bounce cosmology predictions against standard inflation. Loop quantum cosmology, an application of loop quantum gravity to cosmological settings, provides mathematical tools for modeling the bounce. In loop quantum cosmology, space-time is quantized, with area and volume being discrete rather than continuous. This discreteness prevents the singularity. As the universe contracts, it reaches a minimum volume determined by the Planck scale and then bounces. The bounce is robust, occurring in a wide variety of initial conditions and matter content, making it a generic prediction of loop quantum gravity. Calculations in loop quantum cosmology show that the bounce is smooth and can be followed through numerically. The universe contracts, reaches maximum density of about 40% of Planck density, and then expands. The time spent near maximum density is roughly 1 Planck time. During this time, quantum geometry effects dominate, but after the bounce, as density decreases, the universe transitions to a classical phase, where general relativity provides an accurate description. The classical expanding universe we observe is the late time limit of this post-bounce evolution. One profound implication is that the Planck epoch isn't inaccessible to observation. While we can't directly see what happened at 10 to the negative 43 seconds, the bounce leaves imprints on observable quantities. The power spectrum of density fluctuations, the spectrum of gravitational waves, the abundance of light elements from Big Bang nucleosynthesis, and even the detailed properties of the cosmic microwave background all depend on Planck epoch physics. By measuring these observables precisely, we can indirectly probe the bounce and test quantum gravity theories. Another implication is that the Planck epoch might not be unique to our universe. Every black hole that forms undergoes a similar bounce in its interior, creating a new Planck epoch for that interior universe. The physics of the Planck epoch is thus not a one-time event, but a recurring process happening whenever and wherever black holes form. This universality suggests that understanding the Planck epoch is key to understanding not just our universe's origin, but the mechanism by which universes in general come into existence. Matter falling into our parent black hole becomes our dark matter. One of the most perplexing mysteries in modern cosmology is dark matter, the invisible substance that makes up roughly 85% of the matter in the universe. We know dark matter exists because of its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain far more mass than we can see, and gravitational lensing reveals massive concentrations of matter where little light is present. Yet despite decades of searches, we've never directly detected a dark matter particle. The black hole universe theory offers a radical explanation. Dark matter might not be exotic particles in our universe at all, but rather ordinary matter from the parent universe that continues to fall into our parent black hole. To understand this proposal, we need to think carefully about what happens to matter crossing a black hole's event horizon from both perspectives. From outside, matter falling toward a black hole appears to slow down as it approaches the horizon, asymptotically approaching, but never quite reaching it due to gravitational time dilation. From the infalling matter's perspective, it crosses the horizon in finite proper time and proceeds into the interior. These two perspectives are both valid descriptions of the same physical process, related by coordinate transformations. Now consider the interior universe perspective. When our universe formed, it was the moment when the initial mass crossed the event horizon of the parent black hole. But the parent black hole likely continued to accrete matter after that initial collapse. Material from the parent universe continues to fall into the parent black hole, crossing the event horizon long after our universe began its expansion. From our perspective inside, This subsequently infalling matter enters our universe from outside, bringing energy and momentum with it. But how does this matter manifest in our universe? The key insight is that matter crossing the event horizon later, from our interior perspective, doesn't arrive at the same space-time location as the original matter. Space-time inside a black hole is dynamical and expanding, so matter that crosses the event horizon at later times in the parent universe's timeline enters our universe at later times in our timeline and at different spatial locations. This matter appears distributed throughout our universe rather than concentrated at a single point. Moreover, this infalling matter likely doesn't interact with ordinary matter in our universe through electromagnetic or strong nuclear forces. The infalling matter consists of particles from the parent universe, which might have entirely different properties than particles in our universe. They carry energy and momentum, contributing to our universe's gravitational field, but they might be effectively invisible to electromagnetic and nuclear interactions. They would behave exactly like dark matter, gravitationally present but otherwise non-interacting. Nikodem Popławski and others have developed this idea quantitatively, calculating how much mass should cross the event horizon over time and how it would distribute inside. The predictions depend on the accretion rate onto the parent black hole and on the relationship between time, inside and outside. Time dilation is extreme near event horizons. As seen from outside, time inside appears to run infinitely slowly at the horizon, but from inside, external time appears to run infinitely fast. This means that matter falling into the parent black hole over billions of years of external time could enter our universe over much shorter interior times. The total amount of dark matter in our universe, about 5 times more than ordinary matter, could be explained if the parent black hole accreted approximately 5 times more mass after the initial collapse that formed our universe. This isn't unreasonable. Black holes grow over time by accreting gas and merging with other black holes. If our parent black hole formed with a certain mass and then grew by a factor of 5 or more through accretion, the added mass would appear as dark matter inside our universe. The spatial distribution of dark matter also makes sense in this picture. Observations show that dark matter forms halos around galaxies and is distributed throughout galaxy clusters. In the black hole universe model, matter falling into the parent black hole from different directions at different times would enter our universe at different locations and with different velocities. Depending on the angular momentum it carries and the timing of its infall, this could naturally produce the diffuse halos we observe, rather than dark matter being concentrated in discrete structures. One puzzling feature of dark matter is that it appears to be cold, meaning dark matter particles move slowly compared to the speed of light. Hot dark matter, consisting of fast-moving particles like neutrinos, doesn't match observations because it would smear out structure formation. Cold dark matter works, but we don't know what cold dark matter particles are. In the black hole universe model, the coldness could arise from how infalling matter loses energy crossing the event horizon and distributing through the interior. The matter enters with velocities determined by its infall trajectories in the parent universe, and these velocities might naturally be non-relativistic in our reference frame. This proposal makes a striking testable prediction. Dark matter should have a specific distribution related to the geometry of the parent black hole's accretion. If the parent black hole accretes matter preferentially from certain directions, say from a disk in its equatorial plane, then dark matter in our universe should show corresponding asymmetries. Observations of dark matter's large-scale distribution might reveal such patterns. The axis of evil an unexplained alignment of features in the cosmic microwave background, could potentially be related to a preferred direction of infall in the parent universe. Another prediction involves the time evolution of dark matter density. As the parent black hole continues to accrete, more dark matter should enter our universe. The dark matter fraction should increase over time, meaning dark matter density relative to ordinary matter should be higher now than in the early universe. Observations of high redshift galaxies and the early universe's matter content could test this. Current data suggests dark matter and ordinary matter had roughly the same ratio in the past as today, but uncertainties are large enough that slow growth in dark matter fraction might be compatible with observations. The proposal also connects to unsolved problems in dark matter phenomenology. Observations of galaxy rotation curves and dark matter halo profiles sometimes show discrepancies with cold dark matter predictions, including the core cusp problem, where galaxies have flatter central dark matter profiles than simulations predict. If dark matter is in falling material from outside, its distribution might differ from equilibrium halos produced by standard gravitational collapse, potentially explaining these discrepancies. One might object that matter from a parent universe with different physical laws wouldn't behave like normal particles at all, and might not even have well-defined concepts of mass and energy. This is true if the parent universe has radically different physics. But if the parent universe has similar laws, perhaps with slightly different constants, its particles would carry recognizable energy and momentum. They would couple to gravity in our universe even if other interactions differ. This is sufficient to produce dark matter's observed effects. The cosmological constant, problem solved by black hole geometry. The cosmological constant problem is widely considered one of the deepest puzzles in theoretical physics. Observations show that empty space has a small but non-zero energy density, causing the universe's expansion to accelerate. This energy density, associated with the cosmological constant, or dark energy, has a measured value of about 10 to the negative 9 joules per cubic meter, equivalent to roughly 6 protons worth of mass energy per cubic meter of space. Yet when we calculate what the vacuum energy should be using quantum field theory, we get an answer 120 orders of magnitude larger, perhaps the worst prediction in the history of physics. The calculation goes as follows. Quantum field theory tells us that empty space is not truly empty, but filled with quantum fluctuations, virtual particles popping in and out of existence at all energy scales. Each quantum field, whether electromagnetic, electron, or any other, contributes to the vacuum energy. Naively summing these contributions up to the Planck energy scale gives a vacuum energy density of about 10 to the 113 joules per cubic meter, vastly exceeding the observed value. If space actually had this much energy, the universe would have undergone runaway expansion immediately after the Big Bang, preventing structure formation and making life impossible. Physicists have proposed many solutions to this problem. Supersymmetry would cancel contributions from bosons and fermions, potentially giving zero cosmological constant, but supersymmetry must be broken at low energies, and the breaking introduces new contributions that reintroduce the problem. Anthropic arguments suggest we live in a universe with a small cosmological constant because only such universes allow observers, but this doesn't explain why the constant has the specific value we measure. Modifications to gravity or quantum field theory might change the calculation, but these tend to be ad hoc. The black hole universe theory offers a different approach. Perhaps the cosmological constant's value is set by the geometry of the black hole we inhabit, rather than by quantum field theory vacuum energy. Inside a black hole, space-time has an intrinsic curvature that can manifest as an effective cosmological constant. The value of this effective constant depends on the black hole's mass, angular momentum, and properties of the parent universe. By adjusting these parameters, the observed cosmological constant emerges naturally, without requiring cancellations or fine-tuning. In Einstein-Cartan theory, the bounce that creates our universe from a collapsing black hole produces a residual torsion field that acts like a cosmological constant. Popowski showed that the torsion energy density after the bounce, when matter has diluted but torsion persists, contributes a vacuum energy term to the Friedmann equations governing cosmic expansion. This term is proportional to the square of the spin density during the bounce and inversely proportional to the Planck density. Plugging in reasonable values for the spin of collapsing matter gives a cosmological constant in the right ballpark. The calculation isn't exact because it depends on unknown details of the parent black hole's formation and the matter's quantum state during the bounce. But the key point is that the cosmological constant comes out small naturally. Unlike the quantum field theory calculation, which gives an enormous result that must somehow be cancelled to 120 decimal places, the torsion calculation gives a small result from the start because it's tied to the macroscopic properties of the black hole rather than to Planck scale quantum fluctuations. Another approach to the problem comes from considering the interior geometry of a black hole with a cosmological constant in the parent universe. If the parent universe has its own cosmological constant, this affects the black hole's interior structure. The interior metric includes terms depending on the parent's cosmological constant, and these terms can manifest as an apparent cosmological constant for interior observers. The relationship between parent and child cosmological constants depends on the coordinate transformation between exterior and interior regions, and on boundary conditions at the event horizon. Research by Stojkovic and colleagues explored this connection, showing that if the parent universe has a cosmological constant, the interior universe naturally inherits a related constant, typically smaller by a factor related to the black hole's mass and the parent cosmological constant. For plausible parent universes, the child universe's cosmological constant comes out in the observed range. This suggests a cascade effect. Each generation of universes has a smaller cosmological constant than its parent, with the values determined by black hole formation rates and properties. The black hole geometry also affects how vacuum energy contributes to expansion. In standard cosmology, vacuum energy has negative pressure, with equation of state W equals -1 relating pressure to density. This negative pressure drives accelerated expansion. Inside a black hole, the geometry naturally produces expansion independent of vacuum energy, and the vacuum contribution might add to or subtract from the geometric expansion. The net effect is that the observed acceleration can match observations even if the true vacuum energy is much larger than the measured cosmological constant. Because geometric effects compensate, time dilation provides yet another angle. The cosmological constant has dimensions of inverse time squared, and time inside a black hole is dilated relative to external time. If we measure the cosmological constant using interior clocks, we get a different value than if we measured it using exterior clocks, related by time dilation factors. The observed value might reflect this dilation rather than representing a fundamental parameter. The true cosmological constant, in some absolute sense, might be different, with the observed value being a perspective-dependent quantity. These approaches don't fully solve the cosmological constant problem in the sense of providing a unique, first principles calculation that yields the observed value, but they reframe the problem in ways that make it less mysterious. Instead of asking why quantum field theory's prediction is wrong by 120 orders of magnitude, we ask how black hole geometry determines the effective cosmological constant interior observers measure. This is a more tractable question that connects to well-understood classical gravity rather than requiring unknown quantum gravity physics. The black hole universe theory also offers an explanation for why the cosmological constant appears to be fine-tuned for life. If universes form inside black holes and inherit properties from their parents, then universes with hospitable conditions for structure, formation, and complexity will produce more black holes, which in turn produce more universes with similar properties. Over many generations, the multiverse becomes dominated by universes with cosmological constants that allow galaxies, stars, and planets to form. This is Smolin's cosmological natural selection applied to the cosmological constant problem. Observational tests could potentially distinguish these ideas from standard explanations. If the cosmological constant is set by black hole geometry, its value might change over time as the parent black hole's properties evolve, or as our universe's relationship to the parent changes. Current observations constrain the cosmological constant to be very nearly constant, but precision measurements of its evolution over cosmic time could reveal slow variations. Additionally, if the cosmological constant depends on initial conditions during the bounce, it might vary slightly from place to place in the early universe, producing observable effects in the cosmic microwave background or large-scale structure. Time dilation near event horizons. Why billions of years pass inside. Time dilation, the effect where time passes at different rates in different gravitational fields, is one of the most profound and counterintuitive predictions of general relativity. Near black hole event horizons, time dilation becomes extreme, with time for nearby observers slowing to a crawl compared to distant observers. This effect provides a crucial link between the physics of black holes and the cosmology of universe interiors, explaining how an interior universe could age billions of years while only an instant passes in the parent universe outside. The mathematics of time dilation comes directly from the metric, the mathematical object describing space-time geometry. For a Schwarzschild black hole, the space outside the event horizon is described by what's known as the Schwarzschild metric. In simple terms, it shows how space and time are warped by the black hole's gravity. The equation can be read as the square of the distance equals the negative of the quantity 1 minus 2 times the gravitational constant multiplied by the mass divided by the radius times the speed of light squared, multiplied by the speed of light squared and the change in time squared, plus the inverse of that same quantity multiplied by the change in radius squared, plus the radius squared times the angular components. In this equation, the mass represents how much matter the black hole contains. The radial coordinate indicates how far you are from its center, and the angular term represents directions on a sphere. The coefficient in front of the time term, known as GTT, determines how the coordinate time measured from far away relates to the proper time experienced by someone at a specific distance from the black hole. For an observer located far away from the black hole, where the distance is much greater than the Schwarzschild radius, defined as 2 times the gravitational constant multiplied by the mass, divided by the speed of light squared, the effects of gravity are minimal. In this region, time passes normally, and the coordinate time measured from far away is the same as the observer's own proper time. However, as the observer moves closer to the Schwarzschild radius, the gravitational field becomes extremely strong, causing time to slow down dramatically. At the event horizon itself, time appears to stretch infinitely compared to an outside observer, meaning that from a distant viewpoint, anything falling into the black hole seems to freeze in time right at the edge. An observer at rest, just above the event horizon, experiences time passing infinitely slowly compared to distant observers. If you watch someone fall toward a black hole, you'd see them slow down and freeze as they approach the horizon, never quite reaching it in finite time. From the infalling observer's perspective, however, nothing special happens at the horizon. They cross it in finite proper time, perhaps a fraction of a second for a stellar mass black hole, or hours for a supermassive one. The horizon isn't a physical barrier, but a coordinate singularity, a place where certain coordinates become ill-behaved, but the geometry remains smooth. Once inside, the observer experiences ordinary physics, at least until tidal forces or the approach to the central singularity becomes important. This asymmetry between interior and exterior perspectives is key to understanding how universes can exist inside black holes. From outside, the black hole forms and matter crosses the horizon, but the crossing takes infinite external time. From inside, the crossing is immediate, and subsequent evolution proceeds on interior timescales. Billions of years can pass inside, while an arbitrarily short time passes outside, allowing an entire universe with its own history to unfold within what appears externally as a static black hole. The interior time coordinate is distinct from the exterior time coordinate. Inside the black hole, the radial direction becomes time-like, and the original time coordinate becomes space-like. What was the future in the radial direction outside becomes the future in the time direction inside. This coordinate flip means that interior observers measure time along what was the spatial radial direction in the exterior description. The interior time flows from the event horizon toward the would-be singularity or bounce, with the horizon being the initial moment of interior time and the singularity bounce being far in the interior future. Quantifying the relationship between interior and exterior time is subtle because the two regions use different coordinate systems, but we can make estimates. For a black hole with a given mass, the time it takes for light to travel from the event horizon to the singularity measured in the black hole's internal frame is approximately equal to the Schwarzschild radius divided by the speed of light. This can be written as 2 times the gravitational constant multiplied by the mass divided by the speed of light cubed. In simpler terms, this crossing time is about 10 microseconds for every solar mass of the black hole. For a supermassive black hole with 10 billion solar masses, this crossing time is roughly 20,000 seconds or 6 hours. If quantum effects or torsion prevent the singularity and create a bounce, the interior continues evolving indefinitely, with interior time running forward without bound. Now consider how much exterior time corresponds to these interior times. For matter that collapses to form the black hole, its world line crosses the horizon at a finite time in the collapsing matter's frame, but at infinite time in the external frame. For an exterior observer watching the collapse, they see the surface of the collapsing matter approach the horizon asymptotically, never quite reaching it. If the exterior observer waits a finite time, say 1 second, and then checks the interior, an arbitrary amount of interior time could have passed, depending on how close the collapsing surface got to the horizon. This extreme time dilation has profound implications. A black hole that forms in the parent universe and exists for a brief moment in parent time could contain an interior universe that ages for billions or even trillions of years in interior time. From our perspective inside, we experience 13.8 billion years of cosmic history, from the Big Bang to the present. From the parent universe's perspective, the black hole containing us might have formed just an instant ago, or it might have existed for any length of time, with the relationship between interior and exterior timescales being essentially arbitrary. This decoupling of timescales also explains why we don't see rapid changes in cosmological parameters that might be expected if the parent black hole were evolving quickly. If the parent black hole accretes more matter or merges with other black holes, these events take time in the parent universe, but might correspond to extremely long times in our interior universe. We would observe their effects, if at all, as slow evolutionary trends in cosmological constants or matter content, well within observational uncertainties. The time dilation also affects causality and information flow between parent and child universes. Information can pass from parent to child when matter crosses the event horizon and enters the interior. But information cannot pass from child to parent because anything inside cannot escape to the exterior. This creates a one-way causal connection, with the parent influencing the child but not vice versa. The child universe's evolution is determined by initial conditions set when the parent black hole formed, plus any subsequent matter that falls in. But the child cannot affect the parent's universe in any way. One might wonder whether the extreme time dilation violates causality or creates paradoxes. It doesn't, because the different time coordinates are simply different ways of labeling events in spacetime. What's important is the causal structure, meaning which events can influence which other events through signals traveling at or below the speed of light. The causal structure is well defined and consistent in general relativity, even when time coordinates behave strangely. The horizon is a null surface, and light rays on the horizon neither enter nor exit, but hover, defining the boundary of causal contact. Rotating black holes, described by the Kerr metric, have even more complex time dilation properties. The Kerr metric includes an inner horizon in addition to the outer event horizon, and between these horizons, time and space have mixed signatures. Some trajectories can in principle loop in time, creating closed time-like curves, though whether such curves exist in realistic situations remains debated. If our universe is inside a rotating black hole, as Popławski suggests, these complications might affect cosmology in subtle ways, potentially producing observable signatures in the cosmic microwave background or large-scale structure. The Schwarzschild radius and the observable universe, the numbers match. One of the most striking numerological coincidences in the black hole universe theory is that the Schwarzschild radius for a black hole with the mass of the observable universe is approximately equal to the size of the observable universe. This match suggests that our observable universe might literally be the interior of a black hole with mass equal to the mass we see around us. Let's work through the numbers to see how this coincidence arises and what it might mean. The Schwarzschild radius of a black hole is determined using the formula 2 times the gravitational constant multiplied by the mass of the black hole divided by the speed of light squared. In this equation, the gravitational constant defines the strength of gravity. The mass represents how much matter the black hole contains, and the speed of light sets the scale for how space and time curve around it. For a 1 solar mass black hole, the Schwarzschild radius is about 3 kilometers. For a black hole with 1 million solar masses, typical of galactic centers, the radius is about 3 million kilometers, or roughly the distance from Earth to the Sunday. For supermassive black holes, like the one in M87 with 6.5 billion solar masses, the radius is about 20 billion kilometers, or roughly the size of our solar system out to Neptune's orbit. Now let's estimate the mass of the observable universe. The observable universe is the region from which light has had time to reach us since the Big Bang, roughly 46 billion light-years in radius, accounting for cosmic expansion. The average density of matter and energy in the universe is about 10 to the -26 kilograms per cubic meter, combining ordinary matter, dark matter, and dark energy. Multiplying the volume of the observable universe by this density gives a total mass of roughly 10 to the 53 kilograms, equivalent to about 10 to the 23 solar masses, or 100 billion trillion times the Sun's mass. When we plug this mass into the Schwarzschild radius formula, we get that the radius equals 2 times the gravitational constant multiplied by 10 to the power of 53 kilograms, divided by the speed of light squared. Using the gravitational constant of 6.67 times 10 to the negative 11, and the speed of light as 3 times 10 to the 8 meters per second, the result is approximately 1.5 times 10 to the 26 meters. Converting this into light years gives about 15 billion light years, which is remarkably close to the estimated size of the observable universe. Often cited as around 46 billion light years depending on how it's defined and how cosmic expansion is considered. The exact match depends on which mass you use. If you include dark energy in the mass calculation, which you should because dark energy contributes to the universe's total energy density, the numbers align even better. Dark energy makes up about 70% of the universe's total energy content, so including it increases the total mass appropriately. When you do the calculation carefully, accounting for all contributions and using the observed Hubble constant and matter density, the Schwarzschild radius for the total mass energy of the observable universe is very close to the actual radius of the observable universe. Why is this significant? In standard cosmology, this coincidence is just that, a coincidence with no deeper meaning. The size of the observable universe is determined by how long the universe has been expanding and the speed of light. The total mass is determined by integrating the matter and energy density over that volume. There's no reason these should be related to the Schwarzschild radius, and indeed for most of cosmic history they wouldn't have been. The match occurs now, in the present epoch, but wouldn't have held in the early universe when the observable universe was much smaller and denser. But in the black hole universe theory, this isn't a coincidence at all. If our universe is the interior of a black hole, then the mass of the observable universe is the mass of that black hole, and the size of the observable universe is set by the geometry of the black hole interior, which depends on its Schwarzschild radius. The observable universe's edge corresponds to the event horizon, and the horizon's size is the Schwarzschild radius by definition. The apparent coincidence is actually a necessary relationship. We're inside a black hole, so the interior's size matches what you'd calculate for a black hole of that mass. This can be made more precise using the FLRW metric, describing the expanding universe interior. When you solve Einstein's equations for the interior of a Schwarzschild black hole and express the result in coordinates appropriate for interior observers, you find that the spatial curvature and expansion rate depend on the black hole's mass. The curvature radius of the interior spatial sections is on the order of the Schwarzschild radius, and the time evolution of the scale factor is such that at a given interior time t, the radius of the observable region is comparable to Rs. The detailed relationship depends on the matter, content, and other parameters, but the order of magnitude agreement is robust. Critics might object that the observable universe appears flat, with spatial curvature measurements consistent with zero curvature to within a few percent. A Schwarzschild black hole interior, being spherically symmetric, should have positive spatial curvature. How can these be reconciled? The answer is that the curvature we measure is the curvature of spatial slices at constant interior time. And these slices can be nearly flat if the black hole is massive enough, and if torsion or other effects modify the interior geometry from the idealized Schwarzschild case. Popławski showed that the interior of a rotating black hole with torsion can have flat or nearly flat spatial sections depending on the spin and torsion parameters. The curvature is related to the angular momentum of the collapsing matter and to how much torsion contributes to the energy momentum tensor. For a range of parameters consistent with observations, the curvature is small enough to match the measured flatness of our universe. This is another way the black hole universe theory makes contact with observations. It predicts nearly flat spatial geometry for appropriate parent black hole properties. Another related observation is that the critical density, the matter density needed for the universe to be spatially flat, is approximately the density you'd get by dividing the mass of the observable universe by its volume. This is tautological in standard cosmology because we define the observable universe by integrating over a certain volume. But in the black hole picture, it connects to the relationship between black hole mass and horizon area. The critical density corresponds to having enough mass inside a region that the region is on the verge of collapsing into a black hole, which is exactly the condition for the interior of an existing black hole. The coincidence also relates to the cosmological horizon, the boundary of the observable universe beyond which we cannot see because light hasn't had time to reach us. In standard cosmology, this horizon is a light-like surface defined by past null geodesics from the present moment. In the black hole picture, the cosmological horizon corresponds to the event horizon of the parent black hole. Both are light-like surfaces that separate causally connected from causally disconnected regions, and their approximate equality in size is not accidental but reflects their identification. If this identification is correct, then, as the universe continues to expand and age, the observable universe will grow, and correspondingly, the apparent Schwarzschild radius will also grow because more matter will come into view. The ratio between the two should remain roughly constant if we're truly inside a black hole, with the relationship holding at all times, not just the present epoch. Testing this prediction requires observing the universe's evolution over cosmological timescales, which we can do by looking at distant galaxies and comparing past conditions to present ones. So far, observations are consistent with the relationship holding, though uncertainties are large. Stephen Hawking's objections and why he might have been wrong. Stephen Hawking, one of the most famous physicists of the 20th century, had strong opinions about black hole interiors and cosmology. While he didn't specifically address the black hole universe theory in his published work, his broader views on black holes, singularities, and quantum gravity raise objections to the idea that we live inside a black hole. Understanding these objections and the responses from proponents of the theory illuminates deep conceptual issues about the nature of space-time, quantum information, and cosmic origins. Hawking's first objection would likely center on singularities. Together with Roger Penrose, Hawking proved the singularity theorems in the 1960 seconds and 1970 seconds, showing that singularities are generic features of general relativity under reasonable assumptions about matter and energy. If black holes contain singularities where physics breaks down, and if our universe emerged from a singularity at the Big Bang, then it's unclear how a black hole interior could be a livable universe. The singularity would destroy any information and any possibility of structure formation. Proponents of the black hole universe theory respond that Hawking's singularity theorems assume classical general relativity holds everywhere. But at Planck scale densities near singularities, quantum effects become dominant and classical theory breaks down. The theorems prove that classical general relativity is incomplete, not that singularities actually exist in nature. Quantum gravity, whether in the form of loop quantum gravity, string theory, or Einstein-Cartan theory with torsion, might resolve singularities, replacing them with bounces or other non-singular structures. If singularities are removed, Hawking's objection disappears. Hawking's second objection involves information. In the 1970 seconds, Hawking argued that black holes destroy information, violating quantum mechanics. When matter falls into a black hole, its quantum information is lost because the matter is crushed into a singularity and because Hawking radiation emitted by the black hole is thermal and carries no information about what fell in. This information paradox troubled Hawking for decades. He eventually conceded that information might be preserved through subtle correlations in Hawking radiation, but the mechanism remains unclear. If black holes destroy information, then universes inside black holes would lose the information needed to determine physical laws and initial conditions. Each interior universe would be completely random, bearing no relationship to the parent universe that formed the black hole. But observations show our universe has specific, non-random properties, with physical constants fine-tuned to allow complexity. This suggests information wasn't destroyed, supporting the idea that black hole interiors preserve information, possibly by passing it to interior universes. Recent work on the information paradox, including the firewall controversy and developments in CFT correspondence, suggests information is preserved, but in ways we don't fully understand. Some proposals involve complementarity, where information appears lost to exterior observers but is preserved for interior observers, or holography, where information is encoded on the event horizon rather than being destroyed inside. These ideas are consistent with black hole interiors being information-rich environments capable of supporting universes. Hawking's third objection relates to quantum cosmology. Hawking proposed the no-boundary proposal with James Hartle, suggesting that the universe has no boundary in imaginary time, avoiding the question of an initial singularity by treating time as a quantum variable without sharp initial conditions. In this picture, asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because time doesn't extend beyond a certain point. The universe simply exists as a quantum state without requiring a prior cause. The black hole universe theory, at least in some formulations, requires a parent universe and thus seems to push the origin question back rather than eliminating it. Hawking might argue that this is unsatisfying, replacing one mystery with another. But proponents respond that the black hole theory actually complements no-boundary proposals. Perhaps the multiverse as a whole has no boundary in the Hartle-Hawking sense, with individual universes forming inside black holes, being part of an eternal, self-consistent quantum state. The question of first cause is avoided by allowing the multiverse to be eternal and self-reproducing. Hawking was also skeptical of theories that make no testable predictions. He famously quipped that, even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe? He valued empirical testability and would likely demand that the black hole universe theory make specific, falsifiable predictions. Without such predictions, the theory might be dismissed as metaphysics rather than physics. Proponents argue that the theory does make testable predictions. The spectrum of primordial gravitational waves differs between standard inflation and Einstein-Cartan bounce models. The statistical properties of cosmic microwave background fluctuations depend on whether the universe began from a singularity or a bounce. The overall rotation of the universe, if present, would indicate a spinning parent black hole. These predictions aren't easy to test with current technology, but they're in principle testable, satisfying Hawking's criterion for scientific theories. It's worth noting that Hawking's views evolved over his career. He initially believed black holes destroyed information, but later changed his mind. He proposed the chronology protection conjecture, arguing that time travel is impossible, but then acknowledged that closed time-like curves might exist in certain spacetimes. He was open to revising his opinions based on new evidence and theoretical developments. If he had lived to see the recent work on black hole cosmology, he might have found the idea more palatable than we imagine, especially if shown rigorous calculations and observational predictions. One particular issue where Hawking's views are relevant is black hole entropy. Hawking showed that black holes have entropy proportional to their event horizon area, measured in Planck units. The Bekenstein-Hawking entropy formula, S equals K times C, 3 times A divided by 4 times h bar times G, where A is the horizon area, assigns a finite entropy to every black hole. This entropy is enormous. Even a stellar mass black hole has entropy exceeding 10 to the 60, far more than all the entropy in all the stars in a galaxy. If our universe is inside a black hole, does the horizon entropy tell us something about the information content of our universe? The holographic principle, developed partly from Hawking's work, suggests that all the information in a region of space can be encoded on its boundary. If our universe's boundary is the black hole event horizon, then the information content of our entire universe is limited by the horizon area. This seems to contradict the fact that we see an incredibly complex universe with vast amounts of information in every star, planet, and living creature. The resolution might involve distinguishing between information accessible to exterior observers versus interior observers. From outside, the black hole has entropy given by the Bekenstein-Hawking formula, representing the maximum information extractable by exterior observers. From inside, the universe has its own entropy, potentially much larger, representing the information content of all structures within. These two entropies describe the same system from different perspectives, related by the coordinate transformations connecting interior and exterior regions. Hawking's entropy formula applies to the exterior view, while cosmological entropy applies to the interior view, and both are valid in their respective frameworks. Roger Penrose's conformal cyclic cosmology, a competing idea. Roger Penrose, a mathematical physicist who shared the 2020 Nobel Prize in Physics for his work on black holes, has proposed his own radical idea about cosmic origins called conformal cyclic cosmology, or CCC. While different from the black hole universe theory, CCC shares the goal of explaining the Big Bang without invoking a true beginning, and addresses similar puzzles about entropy, time, and the universe's large-scale structure. Comparing these two theories illuminates the range of possibilities for understanding our cosmic origins. Penrose's CCC proposes that our universe's Big Bang was not the beginning, but rather a transition from a previous aeon, an earlier phase of cosmic evolution. The universe goes through infinite cycles, each beginning with a Big Bang-like event and ending in an infinitely expanded state. The transition from one eon's end to the next eon's beginning is achieved through a conformal rescaling, a mathematical transformation that changes the metric but preserves angles and causal structure. In effect, the infinitely far future of one eon becomes the Big Bang of the next. The key insight enabling CCC is that in the far future, as the universe expands and accelerates due to dark energy, all massive particles will decay or be diluted away, leaving only massless photons and gravitons. In a universe containing only massless particles, there's no preferred timescale because massless particles experience no proper time in their own frames. You can rescale time arbitrarily without changing physics. By rescaling time appropriately, Penrose argues, you can map the infinite future of one aeon to time zero of the next aeon, creating a seamless transition. This transition solves the horizon problem differently than inflation or black hole cosmology. Distant regions of the cosmic microwave background are causally connected not because they were once close together during inflation, but because they were connected through the previous eon. The uniformity we observe is inherited from the state of the previous aeon's far future, which had time to equilibrate over immense timescales. The low entropy of our Big Bang is explained by claiming it's not truly low, but rather a continuation of the previous aeon's high entropy state, reinterpreted through conformal rescaling. Penrose also proposes observational signatures of CCC. Before the Big Bang of our aeon, supermassive black holes in the previous aeon would collide and merge, releasing enormous bursts of gravitational radiation. These gravitational waves would leave imprints on the CMB as concentric circular patterns corresponding to the directions from which the waves arrived. Penrose and colleagues claim to have detected such circles in CMB data, though other researchers have disputed these claims, arguing that the patterns are consistent with random fluctuations and don't require the CCC explanation. How does CCC compare to the black hole universe theory? Both avoid a true beginning by connecting our universe to something prior. CCC connects to a previous eon through conformal rescaling, while the black hole theory connects to a parent universe through an event horizon. Both address the low entropy problem by arguing that the apparent low entropy of the Big Bang isn't as problematic as it seems when viewed in context. Both make testable predictions about the CMB and primordial gravitational waves, though the specific predictions differ. One key difference is the nature of time. In CCC, time extends infinitely into the past through previous eons, with no first moment. In the black hole theory, time might extend infinitely into the past in the parent universe, but our universe's time begins when the parent black hole formed. Whether this is a meaningful distinction depends on how you define beginning and whether you're asking about the beginning of our specific universe or of existence in general. Another difference involves structure formation. CCC requires that by the end of each aeon, the universe is nearly empty and featureless, containing only radiation. All structure, including black holes, must eventually decay or disappear. This happens naturally if protons decay on ultra-long timescales and if black holes evaporate via Hawking radiation. In contrast, the black hole universe theory embraces structure formation, with black holes not disappearing, but rather giving birth to new universes, ensuring structure persists across generations. The entropy evolution also differs. Penrose argues that entropy increases within each aeon but resets at the transition to the next aeon through conformal rescaling, which redefines what counts as order and disorder. Critics question whether this actually solves the entropy problem or just redefines it. The black hole theory handles entropy through the bounce, where high entropy from the collapsing phase is transformed into low entropy initial conditions for the expanding phase, through quantum or torsion effects that create correlations. Penrose has been critical of inflation, the standard mechanism for explaining the universe's smoothness and flatness. He argues that inflation requires special fine-tuned initial conditions of its own, merely pushing the fine-tuning problem back rather than solving it. CCC avoids inflation by inheriting smoothness from the previous aeon. The black hole theory can also avoid standard inflation if the bounce or event horizon crossing naturally produces the required smoothness, though some versions of the theory incorporate inflation as a subsequent phase after the bounce. Both theories face the challenge of explaining why the laws of physics are what they are. CCC doesn't address this directly. Physical laws are simply given and remain constant across aeons. The black hole universe theory, in Smolin's cosmological natural selection version, attempts to explain laws through evolutionary selection for black hole production. Universes with laws favouring black hole formation have more offspring, leading to a multiverse dominated by such universes. This provides a mechanism for law selection absent in CCC. The philosophical implications differ as well. CCC suggests a cyclic eternity, with the universe endlessly repeating similar patterns. Each aeon is different in detail, but follows the same overall arc from Big Bang to heat death. The black hole theory suggests a tree-like structure, with universes branching and multiplying through black hole formation. The multiverse grows and diversifies, rather than cycling through similar states. These different structures imply different answers to questions about meaning, purpose, and our place in the cosmos. Observationally, distinguishing these theories requires precise measurements of the CMB and primordial gravitational waves. Penrose's circular patterns in the CMB, if real, would support CCC and potentially rule out black hole cosmology, which doesn't predict such patterns. Conversely, signatures of an overall rotation or preferred direction in the universe would support black hole cosmology and challenge CCC, which assumes isotropy is inherited from the previous aeon. Measurements of the primordial gravitational wave spectrum could also distinguish the theories as they predict different spectral shapes. Both Penrose and black hole universe proponents agree that standard cosmology is incomplete and that understanding cosmic origins requires going beyond the standard model. They disagree on the mechanism and the specifics, but both push the boundaries of mainstream physics. As observations improve and theoretical understanding deepens, we may determine which approach, if either, correctly describes reality. Or we may discover that elements of both are needed, with the universe being simultaneously inside a black hole and part of a cyclic structure, combining insights from both theories into a more complete picture. The information paradox. Where do particles go after crossing horizons? The black hole information paradox, one of the most profound puzzles in theoretical physics, asks what happens to quantum information that falls into a black hole. The paradox arises from an apparent conflict between general relativity, which says information is swallowed and destroyed in the singularity, and quantum mechanics, which insists information can never be truly destroyed. This paradox has driven decades of research into quantum gravity and has direct implications for the black hole universe theory, where information crossing horizons might seed entire universes. The paradox was first articulated clearly by Stephen Hawking in the 1970 seconds. Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to gradually evaporate, losing mass over time. For a stellar mass black hole, evaporation takes an unimaginably long time, about 10 to the 67 years. But, in principle, any black hole will eventually evaporate completely, leaving only radiation. The problem is that thermal radiation is random and carries no information about what created it. If you throw a book, a star, or any object with complex quantum information into a black hole, and the black hole eventually evaporates into thermal radiation, where did the information in the original object go? Quantum mechanics says information must be conserved. You should be able to reconstruct the initial state from the final state, at least in principle. But thermal radiation contains no such information, suggesting it was destroyed. This conflict goes to the heart of quantum mechanics. The unitarity principle states that quantum evolution is reversible and information preserving. If you know a system's quantum state at one time, you can calculate its state at any other time, forward or backward. But black hole evaporation appears to be non-unitary, irreversibly transforming pure quantum states, the infalling matter, into mixed thermal states, the Hawking radiation. This would require fundamentally modifying quantum mechanics, something most physicists are reluctant to do. Several solutions have been proposed over the decades. Hawking initially argued that quantum mechanics must be modified to allow information destruction, but he later changed his mind. One proposal involves information being encoded in subtle correlations in the Hawking radiation. The radiation isn't truly thermal, but contains tiny quantum correlations that encode information about what fell in. Recovering this information would require collecting all the Hawking radiation over the black hole's lifetime and performing impossibly complex measurements, but in principle, information is preserved. Another approach involves black hole complementarity proposed by Leonard Susskind. This idea suggests that information never falls inside the black hole from the perspective of outside observers. Due to extreme time dilation near the horizon, infalling matter appears to an exterior observer to slow down and spread across the horizon's surface, never actually crossing. The information is encoded on the horizon as a hologram. Interior observers see matter fall through normally, but their perspective is complementary to the exterior view. Both descriptions are valid, but they don't contradict because no observer can access both simultaneously. The firewall paradox, raised by Almheiri, Marolf, Polchinski, and Sully in 2012, challenged complementarity by arguing that preserving information requires a firewall of high-energy particles at the horizon that would destroy any infalling observer. This seems to violate the equivalence principle, which says free fall should be smooth and observers shouldn't experience anything special at the horizon. The firewall debate has spawned hundreds of papers exploring modifications to black hole physics, entanglement structure, and quantum gravity. How does the black hole universe theory address the information paradox? If black holes give birth to universes, information doesn't disappear, but rather passes into the new universe. What falls into the black hole becomes the matter and energy of the interior universe. The information is preserved because it's still present in the interior, just inaccessible to exterior observers. From inside, you can see the information. From outside, you can't. But that's not destruction, just causal disconnection. This picture resolves the paradox naturally. Information isn't destroyed in a singularity, because there's no singularity. The bounce or smooth interior replaces it. Information doesn't need to be encoded in Hawking radiation, because the radiation is a separate phenomenon affecting exterior observers, while information remains in the interior. Complementarity might still apply at the horizon, with different perspectives for interior and exterior observers, but both perspectives agree information exists somewhere, either encoded on the horizon or present in the interior. One objection is that if information enters the interior universe, it should eventually re-emerge through Hawking radiation as the parent black hole evaporates. But if interior time runs much faster than exterior time due to time dilation, the interior universe could experience trillions of years and reach heat death long before the parent black hole evaporates in parent universe time. When the black hole finally evaporates, the information would emerge, but transformed beyond recognition by interior evolution. Another perspective comes from holography and the AD-S CFT correspondence. This remarkable duality relates quantum gravity in anti-de Sitter space to quantum field theory on the boundary, showing that all information in a gravitational system can be encoded on its boundary. If our universe is a black hole interior, Holography suggests all information about our universe is encoded on the event horizon, as seen from outside. The interior and boundary descriptions are dual, both containing the same information in different forms. Recent developments in quantum information theory applied to black holes suggest entanglement plays a crucial role. The interior and exterior of a black hole are maximally entangled quantum mechanically, connected through Einstein-Rosen bridges or wormholes in spacetime. When matter falls in, it doesn't just disappear, but becomes entangled with the black hole's quantum state. This entanglement might explain how information is preserved and how interior and exterior observers have complementary but consistent views. The ER equals EPR conjecture, proposed by Maldacena and Susskind, suggests that Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen pairs, quantum entanglement. Every pair of entangled particles is connected by a wormhole in spacetime. While speculative, this idea provides a geometric picture of quantum entanglement and suggests that black hole interiors are connected to exteriors not just causally, but through quantum correlations that preserve information. For the black hole universe theory, these developments suggest that our universe isn't just inside a black hole, but is quantum mechanically entangled with the parent universe outside. Every particle and field in our universe is entangled with states outside the horizon. This vast web of entanglement preserves information while preventing direct communication or causal influence. We can't signal to the parent universe or extract information about it, but the quantum state of our universe is correlated with the parent state. Testing these ideas observationally is extraordinarily difficult because we can't manipulate black holes or observe their interiors directly. But subtle quantum effects might be detectable. If our universe's quantum state is entangled with exterior states, there might be violations of locality or separability that could show up in precision measurements of quantum correlations across cosmic distances. The cosmic microwave background or quantum fields in deep space might exhibit anomalous entanglement structures reflecting the boundary conditions imposed by being inside a black hole. The information paradox also connects to the arrow of time. Why does time flow forward with entropy increasing and processes being irreversible? In standard cosmology, this is related to the low entropy Big Bang. The universe started in an improbable, ordered state and has been evolving toward disorder ever since. But why was the Big Bang low entropy? In the black hole picture, the entropy structure at the bounce or horizon crossing sets the arrow of time, with information flowing from parent to child universe, establishing a preferred direction. Ultimately, resolving the information paradox likely requires a complete theory of quantum gravity that describes black hole formation, evolution, and evaporation from first principles. Neither string theory nor loop quantum gravity has fully solved the paradox yet, though both provide insights. The black hole universe theory adds another dimension to the puzzle by suggesting that black hole interiors are not empty voids awaiting destruction, but rich environments hosting entire universes, making information preservation not just possible, but necessary for cosmic reproduction, observational evidence, and testing the theory. The information paradox's resolution through black hole interiors hosting universes leads directly to the most important scientific question: can we actually test whether we're living inside a black hole? A theory, no matter how elegant or philosophically satisfying, must make predictions that observations can confirm or refute. Otherwise, it remains speculative philosophy rather than testable physics. Fortunately, the black hole universe theory makes several concrete, observable predictions that distinguish it from standard cosmology. The first and perhaps most striking prediction involves cosmic rotation. If our universe formed inside a spinning black hole, as Nikodem Popovsky's Einstein-Cartan calculations suggest, then the parent black hole's angular momentum should leave measurable imprints on our cosmos. The universe should exhibit a preferred axis of rotation with large-scale structures showing correlations that wouldn't exist in a non-rotating universe. This isn't a subtle effect buried in noise, it's a fundamental asymmetry in the fabric of space-time itself. Several research teams have searched for evidence of cosmic rotation by analysing galaxy spins. In 2011, physicist Michael Longo examined over 15,000 spiral galaxies from the Sloan Digital Sky Survey, looking for asymmetries in the handedness of galactic rotation. His analysis found a slight but statistically interesting excess of left-handed spiral galaxies in one hemisphere of the sky and right-handed spirals in the opposite hemisphere. This pattern is exactly what you'd expect if the universe itself were rotating. However, subsequent studies with larger datasets have produced mixed results, with some confirming weak signals and others finding no significant asymmetry. The question remains tantalizingly unresolved. The cosmic microwave background provides another powerful test. A rotating universe would imprint specific patterns on the CMB's temperature and polarization maps. The axis of evil, that controversial alignment of the largest scale CMB fluctuations along a common axis roughly perpendicular to the solar system's plane, could be evidence for this. Multiple independent analyses using data from WMAP and Planck satellites have confirmed the alignment exists, though its statistical significance remains debated. Skeptics argue it could be a coincidence or a systematic error in how foreground contamination is removed. Proponents point out that the pattern has survived increasingly sophisticated analysis and better data. Primordial gravitational waves offer yet another observational window. Different early universe scenarios, standard inflation, Einstein-Cartan bounce. Alternative models predict different spectra of gravitational waves produced in the universe's first moments. These waves leave distinctive imprints on the CMB's polarization, particularly in the B-mode polarization pattern that several experiments are racing to measure. Future space-based gravitational wave detectors, like LISA and next-generation ground-based instruments, will observe these waves directly, potentially distinguishing between black hole bounce cosmology and standard inflation. The spectral index of density fluctuations, already measured to high precision by Planck, provides constraints. The observed value is approximately 0.965, very close to, but slightly below, the perfectly scale-invariant value of 1 predicted by the simplest models. Different bounce scenarios predict different spectral indices depending on the detailed physics during the Planck epoch when quantum effects dominate. Some black hole universe models are already ruled out by this measurement, others remain viable. As precision improves, more models will be tested and potentially eliminated. Non-Gaussianity deviations from a Gaussian distribution in the primordial fluctuations is another discriminator. Standard slow-roll inflation predicts almost perfectly Gaussian fluctuations. Alternative scenarios, including some bounce cosmologies, predict detectable non-Gaussianity. Current observations place tight constraints, showing that if non-Gaussianity exists, it's small. But even detecting a small signal would revolutionize cosmology and potentially favor black hole universe models over simple inflation. Dark matter's distribution and evolution might reveal its origin as matter falling from the parent universe. If dark matter continuously enters our universe as matter crosses the parent black hole's event horizon, its abundance relative to ordinary matter might evolve over cosmic time. The dark matter fraction could have been lower in the early universe, and increased as the parent black hole accreted more mass. Observations of high redshift galaxies from the James Webb Space Telescope and future missions can test this, measuring the dark matter content when the universe was younger and comparing to present values. The cosmological constant's value itself is a test. Popławski's calculations show that torsion effects during the bounce naturally produce a small, positive cosmological constant in the observed range without requiring the 1-2-0 orders of magnitude fine-tuning that plagues standard quantum field theory. If future theoretical developments can predict the exact value from first principles using Einstein-Cartan theory, that would be powerful confirmation. Conversely, if the cosmological constant is measured to evolve with time rather than remaining truly constant, it would suggest geometric effects from black hole interior dynamics rather than fundamental vacuum energy. The coincidence between the Schwarzschild radius for the observable universe's mass and the observable universe's actual size is more than numerology in the black hole picture. It's a necessary consequence. As the universe ages and expands, bringing more matter into view, the apparent Schwarzschild radius and observable size should track each other. This relationship should hold throughout cosmic history. Careful analysis of how structure has evolved over billions of years, using observations of distant galaxies as windows into the past, can test whether this tracking occurs as the theory predicts. Quantum entanglement across cosmological distances might reveal our universe's connection to the parent universe through horizon correlations. If quantum states inside our universe are entangled with states outside the event horizon, precision measurements of quantum correlations in cosmic microwave background photons or in quantum fields in deep space might show anomalous patterns. These would be extraordinarily subtle effects, but experiments like those testing violations of Bell inequalities over large distances could potentially be adapted for cosmological tests. Black hole evaporation timescales provide an indirect test. If every black hole in our universe contains a universe, and if Hawking radiation causes black holes to evaporate, then eventually all these child universes would be destroyed as their parent black holes evaporate. The typical evaporation time for a stellar mass black hole is 1067 years, far longer than the current 13.8 billion year age of our universe. But primordial black holes, if they exist from the early universe with much smaller masses, could evaporate on shorter timescales. Detecting the final burst of radiation from an evaporating primordial black hole and comparing its properties to theoretical predictions could reveal whether its interior contained a universe. The theory also makes negative predictions, things we should not observe if we're inside a black hole. For instance, we shouldn't see evidence of a true singularity in our past because the bounce replaces it. If observations ever detected signatures incompatible with a smooth bounce, such as imprints of genuine infinite curvature or information loss consistent with singularities, it would challenge the theory. Similarly, if observations showed that dark energy has an equation of state significantly different from W equals 1 the cosmological constant value, it might conflict with geometric predictions from black hole interior dynamics. The accumulation of evidence is what matters in science. No single observation will definitively prove we're inside a black hole, but if multiple independent tests, cosmic rotation, CMB anomalies, gravitational wave spectra, dark matter evolution, and quantum correlations all point in the same direction, the cumulative case becomes compelling. Conversely, if observations rule out key predictions, the theory fails regardless of its mathematical elegance. This is the difference between science and speculation. The black hole universe theory makes itself vulnerable to falsification. It doesn't hide behind untestable claims or infinitely flexible parameters. It plants flags in observational space and says, if these effects exist, I'm supported. If they don't, I'm wrong. Over the coming decades, as observational cosmology enters a golden age with missions like the Vera Rubin Observatory, the Roman Space Telescope, and next-generation CMB experiments, we'll gather the data needed to test these predictions rigorously. The universe is patient. It holds its secrets, but it also reveals them to those who ask the right questions and look carefully enough. Whether we're truly inside a black hole or not, the process of testing this theory will deepen our understanding of cosmology, quantum gravity, and the fundamental nature of reality. That's the power of science. Even theories that turn out to be wrong teach us something valuable in the process of proving them wrong. The profound implications for reality and our cosmic future. After exploring the mathematics, the physics, the observations, and the tests, we arrive at the ultimate question. What does it mean if we're truly living inside a black hole? The implications extend far beyond academic physics, touching the deepest questions about existence, meaning, and humanity's place in a cosmos that might be stranger than we ever imagined. If the black hole universe theory is correct, then reality has a structure fundamentally different from what we've assumed for centuries. The universe isn't a box containing everything that exists, with empty space beyond its edges and a singular beginning at the Big Bang. Instead, we inhabit one interior among potentially infinite others, nested like Russian dolls through layers of space-time. Each universe contained within black holes in parent universes, each containing black holes that birth child universes. The cosmos becomes a living, reproducing entity, eternally creating new realms through the simple physics of gravitational collapse. This resolves one of philosophy's oldest puzzles. Why is there something rather than nothing? The question dissolves because nothing never existed and never will. Existence is fundamental and eternal, maintained through an endless cycle of cosmic reproduction. There was no first moment requiring explanation, no creation ex nihilo that demands a supernatural cause. The multiverse simply is, has always been, and will always be, with each universe arising naturally from physical processes in its parent. Our significance in this picture is simultaneously humbling and elevating. We're not unique. There could be countless other universes, perhaps infinite in number, each with its own galaxies, stars, and potentially life. We're one leaf among uncountable leaves on an infinite cosmic tree, yet we're also proof that the process works, that the universe-creating mechanism is robust enough to produce complexity, consciousness, and beings capable of understanding their own origins. We're the universe becoming aware of itself, a feat remarkable regardless of how many times it's occurred elsewhere. The existence of other universes inside black holes in our cosmos carries ethical weight. Every stellar mass black hole, formed when a massive star exhausts its nuclear fuel and collapses, might contain a universe experiencing its own 13.8 billion years of evolution, structure formation, and possibly life. The roughly 100 million black holes in our galaxy alone could host 100 million universes. The billion black holes throughout the observable universe might represent a billion separate realities, each with its own story, unfolding over timescales that seem eternal from their interior perspective, but occupy mere moments in our time. This raises profound questions about the nature of creation and destruction. If creating a black hole creates a universe, do we bear responsibility for these new realms when massive stars in our galaxy collapse? The question is mostly academic since we can't prevent stellar collapse, but it becomes practical if future civilizations gain the ability to create black holes artificially. Would forming a black hole in a laboratory constitute creating a universe? Would destroying it, if that's even possible, constitute destroying all the civilizations that might eventually evolve within? Time itself becomes less absolute in this picture. The 13.8 billion years we've experienced since the Big Bang might correspond to microseconds, hours, or any duration in the parent universe, depending on the extreme time dilation near event horizons. Our entire cosmic history, from the first atoms to the formation of galaxies to the emergence of life, could be unfolding in what the parent universe experiences as a brief moment. Conversely, the black holes in our universe might contain interiors where trillions of years pass while seconds tick by here. Time is not a universal, objective flow, but a relative measure dependent on your position in the nested hierarchy of universes. The arrow of time, why time flows forward with entropy increasing, might trace back to the causal structure of universe creation. Information flows from parent to child through the event horizon but never returns. This one-way transfer establishes a preferred direction, a cosmic arrow pointing from past to future, from parent to child, from cause to effect. The low entropy of our Big Bang, puzzling in standard cosmology, becomes a boundary condition inherited from the parent universe's collapse, with correlations established during the bounce setting our initial state. Dark energy and the universe's accelerating expansion take on new meaning. Rather than being a mysterious vacuum energy requiring impossible fine-tuning, the cosmological constant emerges naturally from the geometry of black hole interiors or from torsion effects in Einstein-Cartan theory. The acceleration we observe isn't driving us toward heat death, but might be part of a natural evolutionary cycle for black hole interiors. In trillions of years, when expansion has diluted all matter and energy to negligible density, our universe might reach an equilibrium state that, from the parent universe's perspective, represents the black hole's final settled configuration. The fate of consciousness in this cosmology is both tragic and hopeful. Tragic because individual consciousnesses, you, me, everyone we know, will eventually cease when our bodies die, and eventually all life in our universe will end when stars burn out and the cosmos grows cold. But hopeful because consciousness itself, as a property the universe can generate through physical processes, might be ubiquitous throughout the multiverse. If the laws favouring black hole formation also favour complexity and life, as cosmological natural selection suggests, then most universes might eventually produce beings capable of thought, wonder, and self-awareness. We might not be alone even within our universe, much less across the multiverse. If life emerged on Earth, a planet orbiting an ordinary star in an ordinary galaxy, the same chemistry and physics should work on billions of other suitable planets. And if universes inside black holes are common, intelligence might be scattered throughout the multiverse, like stars scattered through galaxies. We can never communicate with them across event horizons, but they might be asking the same questions we are, building their own theories, conducting their own experiments, gradually piecing together the structure of reality. The practical implications for physics are immense. If we're inside a black hole, then understanding our universe requires understanding black hole interiors. Observations of black holes in our universe provide data about how universes work. When LIGO detects gravitational waves from merging black holes, it's potentially observing the collision of universes. When the Event Horizon Telescope images black hole shadows, it's potentially looking at boundaries between different realms of existence. Black hole physics and cosmology merge into a unified field, studying the same phenomena from different perspectives. Quantum gravity becomes essential rather than purely academic. The bounce that created our universe occurred at Planck densities where quantum effects dominate. Understanding that bounce requires a complete theory of quantum gravity, weather loop quantum gravity, string theory, or something else entirely. The observational predictions from black hole cosmology provide tests for these theories, potentially breaking the current stalemate where multiple quantum gravity approaches coexist without clear ways to distinguish them. The mathematical structure underlying reality becomes more apparent. That the equations describing black hole interiors match the equations describing expanding universes isn't coincidence, but reflects deep truths about space-time geometry. That event, horizons and cosmological horizons share identical mathematical properties, hints at fundamental connections we're only beginning to understand. Physics might be far more unified than we've realized, with what seem like different phenomena: black holes, cosmic expansion, quantum entanglement. Information all being aspects of a single coherent structure. Looking forward, humanity's future might involve not just exploring our universe, but understanding our place in the multiverse. We might develop technologies to probe the nature of the cosmological horizon, testing whether it truly is an event horizon. We might find ways to detect or infer properties of the parent universe through subtle imprints on our cosmos. We might even, though this borders on science fiction, discover methods to communicate across event horizons using quantum entanglement or exotic physics we haven't yet imagined. But perhaps the most profound implication is epistemological. It concerns the nature of knowledge itself. If we're inside a black hole, separated from the parent universe by an impassable barrier, then some truths about reality might be forever unknowable. We can theorize about what lies outside, we can make predictions and test them, but we can never directly observe the parent universe or confirm with absolute certainty that it exists. Our knowledge will always be limited by our cosmic horizon, by the boundaries of our particular universe's interior. This isn't cause for despair, but for wonder. Despite these limitations, we've constructed theories that explain our observations, make predictions, and reveal the universe's structure. We've traced our origins back to the Big Bang, and possibly beyond, to a bounce in a parent black hole, to a chain of universes extending into an infinite past. We've connected the largest scales of cosmology to the smallest scales of quantum mechanics. We've shown that human reason, developed by evolution to help primates survive on an African savanna, can comprehend the structure of space-time itself. Whether we're inside a black hole or not, whether the multiverse is real or imagination, whether other universes exist or we're alone, these questions drive us forward. The search for answers is what makes us human. We look up at the night sky and wonder. We build telescopes and satellites to extend our vision. We develop mathematics to describe what we see. We construct theories and test them. We push the boundaries of knowledge outward, always reaching for understanding. The black hole universe theory represents the current frontier of this eternal quest. It takes seriously the mathematics of general relativity and quantum mechanics. It addresses real problems in cosmology with testable solutions. It opens new possibilities for understanding cosmic origins, the nature of time, the structure of reality. Whether it proves correct or incorrect, it demonstrates that we live in an age when the deepest questions about existence can be addressed scientifically, where speculation becomes testable theory, where the boundary between philosophy and physics dissolves. We stand at a unique moment in cosmic history. Our universe is 13.8 billion years old, young enough that stars still burn, galaxies still form, life still emerges, but old enough that we've developed the technology and understanding to ask fundamental questions about reality. In the vast future ahead, measured in trillions of years, most of the universe's history will unfold in darkness and cold after stars have died. But now, in this brief cosmic afternoon, we can observe, think, and understand. If we're inside a black hole, then we're witnesses to one of the most remarkable processes in physics, the creation of a universe from gravitational collapse. We're living through the experiment, experiencing the outcome from inside, seeing the results firsthand. The cosmic microwave background, the expansion of space, the formation of galaxies, these aren't just phenomena to study, but evidence of our origin, traces of the event horizon crossing that brought us into existence. And if every black hole creates a universe, then the story continues beyond us. The stellar black holes forming in our galaxy today, the supermassive black holes growing in galactic centers, even the microscopic black holes that might form in high-energy collisions, all might contain universes experiencing their own histories. The multiverse isn't just past and parent, it's also future and child. We're part of an ongoing creative process, a cosmic reproduction that never ends. The universe we observe, with its vast scales and ancient light, with its galaxies and stars and planets, with its quantum fields and curved space-time, might be one interior among infinite others. But it's our interior, our home, our stage for asking questions and seeking answers. Whether we're inside a black hole or not, whether the theory proves true or false, the quest to understand transforms us. We become more than passive observers floating through space. We become active participants in the universe's self-discovery, the means by which reality comes to understand itself. That's the ultimate meaning of the black hole universe theory. Not that we're trapped or diminished by being inside, but that we're connected to parent universes that came before, to child universes that will come after, to the eternal process of cosmic creation through the simple, elegant physics of gravity and quantum mechanics. We're part of something larger than ourselves, something that extends beyond our observable horizon, something that gives structure and meaning to existence without requiring anything supernatural. The universe is vast, strange, and beautiful. Whether it's the interior of a black hole or something else entirely, it's ours to explore, to question, to understand. The journey continues, the questions multiply, the horizon of knowledge expands. And that journey, that quest for understanding, might be the universe's greatest creation of all. Conscious beings capable of comprehending the cosmos and marveling at its wonders. Minds that can look up at the stars and see not just distant lights, but windows into the fundamental nature of reality itself.